to that. We have a fully packed afternoon with lots of interesting activities. We will look a little bit with Matthias into Stack and the background so that you understand our common metadata format. Then we look a little bit into the different file formats. Tina will present that. Then we will have a break. Then we will look into some concrete implementations done in OpenEO and with a pure Pangeo stack so that you can see for the same application different ways of approaching it and how this correlates to each other. Finally, we will look a little bit into scaling and large-scale processing and how this is working on Pangeo and OpenEO side. A little bit, Jerome will give an overview of under the hood from the Vito backend implementation to this end, and Lorenzo will present, or Tina will, sorry. Whoever wants can present about that. We don't have to settle it now. You still have about 2 hours to decide, but and a coffee break in between to do so. Maybe just as a reference, so again, we have prepared on Git the whole material that we present here today to you. So you can find the link on the explanation side here. One of the things you're supposed to do were registering your account so that you can work on the cloud infrastructure for these exercises. That you can do following the link over here. Is there anyone who has not yet registered for an account and needs one for this session? Then I think Benjamin can help you, and also Lorenzo. We have some backup accounts here. Yeah.
So if you do not have access yet, please raise your hand because we will hand over some of the.
Very good. So accounts are coming. Explanation is also, yes?
Will there be anything necessary that is not provided within the GNOME repository?
I don't think so.
That
That depends if you have for the scalability exercises, if you're also...
If you already cloned it, or it is already cloned, you have everything.
Yes. If you have it on your own Jupyter environment, which is not the one online, you might not have the direct access to the scalable Dask cluster, though. Right?
But you are using this Pangeo.
Sorry?
Which infrastructure are you using?
The infrastructure, are you using your own setup? Okay.
Following along everything.
Okay, you will be able to do everything, but be aware that we are scaling. Or maybe we can have the microphone. So we are doing some exercises where the plan is to scale using a Dask gateway. If you are not on the infrastructure, on your local computer, you don't have a Dask gateway. Yeah? So the scaling will be limited, but we are showing in the notebooks on how you can do it on your own local computer.
Yes. Okay.
Sorry.
No worries. Thanks for this clarification. Generally, again, this repo that we are talking about is this one here. Maybe also a huge shout out to everyone who has worked on this. So there were quite a lot of people involved in creating all the material here for you today. Here you can see, I think now everyone is online there. So thanks to all of these people. Then I guess we can get started with the first talk of Matthias, or is there anything?
We will see the setup after the we don't need a setup. So you can make your presentation, and then we will check again the access to the infrastructure for the hands-on. Okay, before the check. But you can go, the floor is yours.
Thank you. All right. Good afternoon, everyone. This is the introduction to Stack. First of all, who has heard about Stack so far? Oh, that's good. And who has worked with Stack?
That's the same amount of people, it seems. Great. All right, so the introduction might not be as relevant for you right now, but let's see. So, first of all, why Stack? Well, you may recognize all these portals, or you may not, probably you may not. But there were like a lot of data portals out there. You could get your data there, but you had to register all the time. They have different APIs. All the UIs look differently, right? The APIs were different. Sometimes you had the cloud cover from 0 to 1. Sometimes it was different, right? And this was just difficult for people to understand and to get used to. So the aim was to get, well, something that unifies that, so that you only need it once to learn it once, and then you don't need to go to all these portals and download your data, right? And then the idea was to, well, write a specification, metadata model, and an API specification on top of that, and that is now what Stack is. So what is Stack? Stack is a suite of specifications and software. So that's the specifications and software on top. All what was done with the specification work was tested directly with software. So there were always server, client, and other implementations around that. So it was always like a bottom-up approach, pretty much. And it builds, like the specifications are built into two parts. It's a Stack specification that describes geospatial and or temporal data through interlinked static JSON files. So you can just put them on an S3 bucket, and then they point to each other, and you can just like, it's a network of files that describe the data. You don't need any like server implementation at that point. If you want and want it more dynamic, there is the Stack API specification, which adds all the dynamic elements to the Stack metadata model, which adds search, aggregation, transactions, and it makes Stack really useful for like very wide and big use cases where you can't really like go through the individual files that are on S3 storage and look through them. So Stack, in short, means, or in the long written thing, is spatial temporal asset catalog. Well, it consists of multiple specifications, as said, and all these specifications are extensible and have numerous extensions. The main focus of Stack at the beginning was search and discovery, right? This is extended over time, and now you can use it for ingestion, for processing, etc. But the main use case was really finding the data that is out there and make use of it. The ecosystem consists of multiple things, right? It's the specifications, it's the data itself that, of course, is published as Stack. There is a lot of tooling, software around it. There are tutorials on the Stack website and elsewhere. And it's, of course, also some kind of a community like the Pangeo community where people just come together and share whatever they need and their experiences. And there are monthly calls for working on Stack. There are bi-weekly calls just to talk through new things and just align each other. But Stack, of course, is also not everything that is going around with metadata, so it's not meant to be a full-fledged metadata standard at the beginning. So it doesn't necessarily replace all your metadata that you have, for example, in the ISO standards, or you have old other formats that you're using. You can still use them and link to them, right? So you don't need to port everything to Stack. You can just still use whatever you had so far and add it on top. It's also not necessarily covering all kinds of data, right? So it started, of course, a lot with raster data. It can be used for like bigger bunches of vector data. But for example, if you like want to expose individual vector data sets, like individual geometry, Stack is just not what you want. You need to go into the OGC APIs, OGC API features, for example. They have APIs that cover exactly for that, and we don't need to mimic that. The Stack specification is what we're talking about first. Just a quick introduction about what elements are in the specification and how you combine them. So the three most important entities, and in the repository they're also like grouped by that pretty much. The specifications are split into these three parts. Are catalog, collection, and item. So the question I get asked most often, what is the difference between the catalog and the collection? Well, First of all, a catalog is a very thin, small thing that just exists pretty much for the static stack catalogs that you place on S3 storage. And because you can't put like everything in one collection in the end, you group that somehow into smaller chunks. So it's some kind of virtual folder that you add to just reduce the size of elements that you get per one file call. That is similar to what you do with pagination in an API, right? But here you can do something like, for example, you group by year and then by month, by day, etc. So an example of a catalog could be all Sentinel-2 imagery for a specific day. Then a collection is basically a catalog with additional metadata that groups a single data set into one part, basically, and says this is very similar, use this as one group of data. And adds extend, license provider information, keywords, and other things. And the example here would be the collection would be, some, for example, all Sentinel-2 L2A data, right? And the item is then the final lowest thing that you can access as a file. That is, for example, a Sentinel-2 capture, a single Sentinel-2 capture with all of the bands that it has. It is GeoJSON as the basis, and then extends that for Stack to add, for example, assets, which we'll talk about later, and is usually for a specific location and date, time, or an interval, right? And then each of these, except for catalog, which has assets, but all the other entities can have both assets and links included. And an asset in an item and a collection is pretty much a single file in the end. So, for example, you could have your data, your Sentinel-2 capture as COG files. There are two options. Usually you have each band as a single COG file, or you have one COG file with all bands included. You can do both in Stack. You just describe it with metadata, and then you know which bands are in the file. So in the case where you have a single COG file, you would just have one asset. Otherwise, you would have, I don't know, if you have 10 bands and 10 files, you would have 10 assets. And links are what do the linking in Stack pretty much, so that you can do the hierarchical structure, that you can link between collections, catalogs, and items, that you can link to related resources like the homepage that describes the data, or to the license information, or to other metadata that you have, right? This is all what is in links. And that is the 5 entities pretty much that you have in Stack and need to know about. This is how a catalog could look like, right? Usually you start with an entry catalog, and then that contains various collections. But it doesn't necessarily need to be all on the same level, right? You can group that as you like. It's flexible. And then from a collection, you can go down to different catalogs. As I said, so for example, if you have Sentinel-2, you could have one level of catalogs that describe years, and then one level down, you have the months per year, and then another level down, you have the days per year, per month and per year, for example. And then you get all the items in the end, right? So it's a browsable, crawlable, big chunk of data, usually as a tree, but could also be more a graph structure in the end. The catalog layout can follow this approach that I've just shown, but there are various best practices online that you can follow. So there is a link in the presentation which we'll share later, so you can click on it and then you can find out how you can structure your catalog ideally. It's not necessarily a tree, as I said, so it can also be interlinked between, so items can interlink between each other, right? So that you have, for example, the information from which item you derived your data. And there are other data types as well, like relation types and links as well, that you can describe where the license is, where the homepage is, where, I don't know, your contact form is, or whatever. Then the stack specification model is extended by various extensions. Just listed a couple of them. There are far more. And a couple of them are more important than others. Depends on the use case often. So for example, in OpenEO, you use a lot of the information in the data cube extension, electro-optical, raster, projection, and SAR, depending on the data type. And then this information is very important for processing, for example. For other use cases, you may need others. You will see that later as well. And these extensions usually define new fields in the stack specification for new domains, for example. So you can have something for point cloud, you can have something for forecasts, for SAR data, for different things. And all these extensions usually are just a README file, a JSON schema and examples, so that you can figure out what exactly this is. This can be used then for validation in the end, etc. So the metadata fields itself are partially in the extensions, but also partially part of the stack specification itself that is called common metadata. So that means you have a single definition of a field that you can define, like the description, for example, a license field, or I don't know, a start and end date time, different things that you can use, and you can use them in every entity. So if it's defined once, you can use it as in a collection, you can use it in a catalog, you can use it in an item, you can use it in an asset, and then also in the links, right? So that is defined once, and then you can use it in different parts of the specification, reuse it, so it's always only once defined. And then there is some kind of a inheritance hierarchy. So if you, for example, define the projection in the item properties, it applies to all the assets that are below it. Sometimes you need to override it, right? A projection, a thumbnail, for example, usually doesn't have a projection. So if you say all my files are in EPSG code, I don't know, 1, 2, 3, right? That applies to all assets. But the thumbnail doesn't have this projection because it's just a PNG file that is not really rectified. Then you can say the projection is null, so not existent. You override it. So there is some kind of hierarchy going on in inheritance. The stack API specification, as I said, adds the dynamic elements to the stack specification, and it is HTTPS and JSON at the core. It is, again, defined as multiple parts, so the core specification just gives you the entry elements to building an API, and then you can add a couple of things on top that you may need. For example, search for items, search for collections, aggregations, transactions, so that you can modify and delete individual elements. And there you usually have a different structure as before. So you see here, beforehand, for example, you could go through, you had a catalog, then you had another catalog, you had a collection, another catalog, an item, and an asset in a row if you go down. In an API, all the catalogs go away, and you pretty much just have the landing page, which is a catalog. Then you can, of course, have collections, and then all the items are below. So as this, you can now search through. You don't need this grouping by catalog anymore, so it's just catalog, collection, item, and then you go to the asset. That is a much faster way to go through it. The API specification, again, is extensible, and while stack, the specification itself, has been released in 2021, the API was a bit later because all the inheritance from OpenGC APIs, which are developing a bit slower, it has now been released in 2023 as stable version. The API can also be extended, as said before. There are various extensions that I named a couple of times now: aggregation, etc., filter, language sort, etc. And these define usually new endpoints to the API specification, new parameters, new behavior in the API that you can add on top of your core API. The ecosystem, briefly going through that, there are a couple of notable clients here that you can use. Somehow this presentation is not the latest version, interesting. Because I marked all the relevant things that we may need here, which is, for example, the Python ecosystem, of course, PyStack client is relevant. in this use case here, you may need Stack Browser to browse through your catalogs, or the QGIS plugin to search through APIs. Servers I removed from the presentation. I'm not sure why this is anyway. So if you want to set up your own, there are pre-implemented APIs in open source that you can use and set up. The most advanced one right now is StackFast API. And there are other notable tools. For this workshop, I think interesting are the ones that are for Jupyter and Xarray. So there are a couple of things that load stack data directly into Xarray. So there's a bridge between them. Xstack, StackStack, IntexStack, ODC Stack, there are various of them. And for Jupyter, there are a couple of things to visualize in the notebook, StackNB and LeafMap for map visualization. A couple of other tools as well, so web mapping libraries, GDAL integration is there as well, validation tools, etc. There are various public APIs that you can use and get data from. Earthsearch is one that exposes Sentinel data, and USGS Landsat is there for Landsat data. There is even a server that exposes data from Mars and other planets, so also pretty interesting. Microsoft Planetary Computer has a wide variety of data that is publicly available. All OpenEO instances expose Stack. They take Stack in and give Stack out, so that is very important here as well. Jeroen will mention it later how that works. And if that's not enough, you can go to Stack Index. There is a long list of catalogs, tooling, and tutorials on Stack Index, so you can browse through there and see what's available. Yeah, and that's not part of the presentation because I'm not sure we have the wrong presentation here. Anyway. Good, that's it from my side, I think. 23 minutes, perfect.
You used actually less than 23 minutes.
Then we have time for questions or so, I don't know.
Yeah, exactly. Are there any
questions?
questions regarding Stack right now? Otherwise, we can. Yeah.
Yeah, maybe I should use the microphone. If you go to the API, the first API slide, you omitted
below?
Basically.
No,
Yeah,
below.
go up, I think. Ah, no, here, yeah,
Yeah.
20, slide 20. You omitted basically here that catalog can have a catalog, right?
There are no catalogs anymore in the API.
Yeah. So is there anything planned to have sub-collections? So basically, if I have, for instance, now, I don't know, orthophotos, and then I have like several collections of orthophotos, do you plan on integrating that?
No, because we're inheriting the collection structure from OGC APIs, and OGC APIs doesn't have this concept of sub-collections. So whenever OGC API will include that, we can add that as well, but otherwise we're restricted what OGC APIs offer us. What you can do, so if the normal structure that we see here is part of OGC API features and Stack API features. You can, of course, we have the link structure in Stack, right? And the landing page is pretty much just a catalog, and you can add additional links to there which point to static files again. So you could do that there, so that you have the normal API implementation, and then you add like static catalog in the background that does whatever structure you want.
Okay, thanks.
Okay, maybe final notice also, we are right now also in the process of bringing both actually Stack and OpenEO into the OGC as community standards. It's maybe also interesting for you that they're right now in the accreditation process, and maybe, I don't know how with Stack you had already some first voting or not?
It's
Soon. Anyways, probably within the next couple of months or so, Stack will come, and a few months later also OpenEO. That's right now in the process of getting into OGC as well. Okay, then I would give the floor to Tina who is somehow stuck.
Okay.
And,
Yeah. Thank you. So, hi everyone, I'm Tina. I will be presenting with Lorenzo. Come on, don't escape. Because this,
So Tina, maybe before you, while you are preparing, we can check who has access to the infrastructure or who still. Only two? So maybe I do it the other way around. Who do not have access to an infrastructure? So you got the username and password with this small piece of paper. And Tina, you will put again the setup instruction. We have a HackMD where we explain how to get to log in.
yes, I'm trying. Oh.
Yeah. But maybe put the HackMD first. Yeah. So first, if you don't have the Wi-Fi, we put the Wi-Fi at the top, the SSID and the password to get access to the Wi-Fi. And then maybe you make it slightly larger for people at the back. Yes. So you can go to this document. It's a shared document where you can also ask questions. And here below, so you can edit. Show maybe how to edit. You have the small pen at the top left, where when you click on the pen, it goes to the edit mode, and it's a markdown. Yeah, so, and here you can write text. So you can add your name here if it is not already there. If you were in the session this morning, your name is probably already there. If not, you can sign up again. And then below, we are showing how to get access to login, how to access to the Pangeo EOSC. So if you don't have access yet, this is what you need to follow.
You can click here to go back to the
yeah. So everyone got access to this HackMD? Who doesn't have access?
We don't see any people writing the name here.
Everyone has
good.
access to the HackMD? Yes. So then you have put your name. Well, good. Some people are writing their name.
Luca.
Perfect. Perfect. Who do not have access to the infrastructure? Do you have a username? Do you need a test user? So the infrastructure is this one. And then when you click on this, if you don't have signed in yet, we will hand you over a test username. But you are already logged in.
Yeah, I will log out. So it's kind of nice.
So who doesn't have a Jupyter Lab open? You should have this now. Do you have it? Who doesn't have it? Okay, but do you have a username and password or? Okay.
I want to change so that screen, I just mirror the screen.
No, but you
because
did
it's
the setup
already
already.
Nightmare to.
Below.
How do I mirror?
You already did this?
Yes. Yeah, I'm coming back. Okay. HackMD. The link to the HackMD is here. HTTPS HackMD at Pangeo, Pangeo-BiDS'23. BiDS, it's I is small I. Sorry about that. We had some people having a problem connection. Yeah.
So we are waiting a few minutes for making sure everyone has access, no?
Yes. And don't hesitate to wave us because we are 1, 2, 3, 4 to help you. So don't be shy to tell us that if there's something not working. And then if you don't have login and password, catch Benjamin because he is the login and password master.
Yeah, I got enough.
Okay.
I think I got enough.
But if you want to make your own account, you can also make your own account. In that case, for the people who want to make own account, you can follow. Oh, great! Follow the setup instruction, and there you have all the registration process for making your account. This one is for connecting to Pangeo, the one that I'm going to show, and the people who also will make the test with OpenEO, how the connection method is also written there. And if you don't want to do anything, don't hesitate to wave to Benjamin so that you have the already ready-made login and password that works on OpenEO and Pangeo EOSC both. Okay, I go
So
back.
just one notice, if you want to register yourself, and when you enroll, we ask you to write a message in the description saying that you are enrolling for a course or you are part of this course, because when we are accepting, we are checking if there is something in the description. And if you don't put anything in the description, you will be denied. It's mostly to avoid having people using the infrastructure for doing some mining, for instance. So, because we are monitoring regularly, but so make sure when you sign in, you put something in the description.
Here.
And the description we have put, Pangeo, OpenEO tutorial, whatever we can recognize, you are part of this community, because this is open to everyone, but this is for doing science or doing research and not for getting money. I think we are all good to start? Good, Tina.
Okay. So once you now I have the mirror, so I don't need to turn my head all the time. That's really nice. Thank you. So I will just once you connect, you select the notebook, and then once you select the notebook, what you can do is
you need to clone the repository.
Yes.
Just to make sure.
So you will normally, when you connect, first of all, you will see a terminal. So who is not familiar with Jupyter Lab? Okay, everybody is perfect. Everybody is very familiar with Jupyter Lab, and then who's not familiar with JIT? Okay, so first of all, once you connect it, you can click the terminal. And once you connect to when you connect to the terminal, normally you would see, it's very small, you will see something like your Juvian and then Jupyter and your login name. So what you have to type is this JIT clone, which was basically just need to copy and paste that today's explanation.
We put it in the HackMD.
Here.
Or here. Yeah.
You just can click this to copy, and then you just need to paste it on your terminal, like that, and then it will copy all your the material for this afternoon. In case you are there this morning, this material is already there. So once you finish once you do the JIT clone, you need to go on the left side, and then you click the file browser, and go and click the Pangeo OpenEO BiDS'23. Go into tutorial, and now we are at part 3. So you click the part 3, and then we will start the explanation using the chunking introduction. So you can double click the chunking introduction, and on the right, and then you can close the file tab like that, and then you can go to the notebook of chunking introduction.
Just checking Do you all have it open?
Don't
Who doesn't
hesitate
have
to
it?
wave and
Who needs help? Well, you are all good. If you need help, we are here to help. Huh? I don't want to do anything, but if I need to, I will jump in. So good, Tina. I think
Yeah.
everyone is here.
so if everybody is fine, so who was there this morning, the part one session, part one? Who was there in the part one? Okay. So part one, there was an example about this X-ray notebook. So this one is basically linked to this X-ray notebook. So about the introduction of X-ray. So in this afternoon, we will more focus on the chunking first, and then afterwards task. And chunking is very important concept for making your process in parallel processing, because basically if you want to parallel process, you have to divide your task. So chunking is basically this basic bits of the basic Lego brick of breaking your task into pieces. So that's what we will explain why this chunking matter, and then how can I read data sets by chunks to optimize the memory usage or parallelization. So our objective of this notebook is learn about chunking and also learn about ZA, which is very linked with chunking for our usage. And also we'll learn about CAN-chunk, to how to use the chunking for NetCDF or other kind of files which is not ZA. And that's it. So I'm supposed to talk about 30 minutes. And of course, don't hesitate to wave and stop or make funny faces so that we know that you're not following or there is something I'm doing something completely stupid. So that Anne or Alejandro can help you from behind, and also I can answer your question from front. And if you are too shy to say anything, you can write your question in the HackMD. There's a question section. You can write it, and Anne or Alejandro or Lorenzo will tell me that, oh, there's a question, then I will try to answer the questions. Okay. So it's a bit small. I don't know how I can do it to make it better, but okay. Probably that's better. Does anybody sees it? Okay. So let's start. So when we are like dealing with large files of the large files and so on, sometimes like with one single PC, you cannot put all your data on your RAM, on your memories. So this is a kind of situation that what we Pangeo ecosystem that we use chunk to help your situation. So X-ray have this lazily chunking loading file system, and then that's kind of like it's will load your files chunk by chunk, bits by bits, and then by reading this data set by like bits by bits, you can process it in a parallel, but you can also load these data only bits and bits so that you don't have memory crash on your data workflow if you chunk it good. And so, how we will process these chunks in the parallel environment? That will be like I will discuss that on the next notebook on like a scaling with task. And then we will explain about this chunk on this one. And then when we, I already said that before, I will not repeat. Okay, so how many of you never heard about ZA? Okay, great. It's good. And so this ZA is basically, it's a reference library in the Pangeo ecosystem to treat these files, like save these files in a chunked form. So that is a form who never heard about NetCDF? Fine, okay. So it's a NetCDF is a format that you can save your data with the metadata, and I will show you afterwards. And then, it's okay, let's see if you know. And then so that the ZA is more like showing, having this netcd file, but in a more explicit ZA chunked format.
I think, Tina, we will see, when you will show the example, it will be easier for people to understand if you have never seen this data format.
Yeah. So this analysis is the same one as the X-ray example this morning, and then we will we will use the data for data, and then this about the data. Like I wanted you to explain this data because it's.
Okay.
Yeah.
Wait a second. These basically are the data coming from the Copernicus Global Land Service. Is a long-term statistics for the entire time series, and is provided. I think that we fetch the data directly from the OpenEO Veto backend, so maybe not too updated, but more or less that's it. During the tutorial that we did 1 year ago, we were using this data to make comparison with the actual data against the time series data. So that's it.
That's right. Yeah. And so we will use this data as an example for this chunking process. And then we will use some of these Python packages, so fspec or S3fs, Xarray and Dask and Kerchunk and GeoPanda and Matplotlib. And these on your Pangeo EOSC infrastructure, we have already installed these packages, so you don't need to install it. But in case you want to try this on your PC, you will need to install these packages. Okay, yes. So this is also about the
It's also from the
in the morning you only use the one time series, but in this example we will use it for some years to show how we scale. So if you are connected and if you have downloaded, you can, for example, try to execute the notebook together at when I explain. I guess that's what you did in this morning. Yeah, right. So first of all, we will load these packages. So which is FG's packages, and then what we do here is like we are loading our data from the cloud storage that we have on EOSC cluster, and then we load this netcd file. And then so if you load this, in the first example this morning, you just loaded one file, right?
Yeah. So here we also have one file.
Yeah.
But the difference here, you are loading from a S3 bucket. So when you are loading from a S3 bucket, we are using this MF dataset. If you remember, for those who were this morning, we downloaded a file locally, which was an etcd file, and we opened the file with xr.open dataset. So it's for one dataset. But here you can open from a bucket from any remote, and this is why you have this MF. Because we are still opening one file. Huh?
And so once you open this file, what you see here compared to the morning, the difference is that here you will see some files which is loaded as a Dask array, and then you see some chunk size here. So what is this? So with this, by like using this OpenMF data set, OpenMF data set, compared to the morning session, which was just using the open data set, we will automatically have some chunk. We automatically have the data set we load is automatically have chunk format. So for example, like you can try out using open data set, or like you can also try this XLA open MF data set and open data set to see how you have like your chunk is appearing or chunk or without any chunks. So this data set, so when we look this data set, so with, for example, if you can also click this part, when this part is, for example, this one, so you will see that there are files are chunked, or these are these files, like you have a lot of lines. That means this one file have really small, it's bits made in the small chunks of bits. So for example, like when it is not chunked, that all the array size, for example, is a 2.2 gigabyte, and then all the one file of the chunk is have like a 1 gigabyte. Whereas if you see here, it is chunked, all the file is like have 15,000 times, like 40,000 times as an array size, but it is chunked in a smaller bits, which is 1,000 times like 3,000. So basically, you make it in a small bits.
Why are the X and Y dimensions reversed in the text and on the graphic?
Why all the
first one
It's because we are using different data set. In this data set, they are already organized in a proper X and Y. And in the example is coming out from another example that was using a completely different system. So it was flipped.
Tina,
That's why it's a good point, but the reason is just a matter of source of two different. Everybody is reusing stuff from different presentation. Yeah.
In this case, with the MFO data set, the data where it loads from was already in different files, right? Or not yet?
In this case, actually.
so that's the
Wait a second. In this specific case is actually just one single file, okay?
yeah.
So usually you use the MF open to create out of multiple files one cube.
But here it was not.
But here it was not. There is another things that I would like to add, and we will talk later. I would suggest that if we are going to use an S3 bucket, using NetCDF file is not optimal. Okay?
Yeah.
So in the later we will see the ZAR file that is.
Okay, and then related to that question, suppose it was consisting of several files, without specifying the chunk size, will it reuse the chunks
Yeah.
as the individual files
Yeah.
were already set?
Yeah,
Right.
that's it. Yes, exactly. Yes. Yeah. So basically, so if you do the open data set, and then basically you don't have a chunk. And then if you do this open MF data science, and then you have these chunks. And then this one example, it's the example of like this one without any chunks. So when we open like several NetCDF file with OpenMF data site, so by default the chunk corresponds exactly what you said. Chunk is corresponding to the entire size of this variable data array that you read from each file. And then so when you want to analyze these like large files, the memory of the computer, that's something which you always need to think. If your memory of the computer is like 16 giga or 30, or you just have small machine that you're running on the cloud that you only have 2 giga of RAM. So you need to think about it and then try to make your data set chunk which fits in this memory. So for example, if you have all this data without chunk, you have this kind of a shape that without any lines. And then with this chunks, like we can have the chunk on, for example, x direction or y direction or time direction, whichever the coordinate or dimension that you want it to have. So when we are using OpenMF dataset, it will use on default each file size as a chunk. But afterwards, would it be really appropriate for the calculation that you want to do afterwards? That's something you need to think about it later. If you need to make some sort or some aggregation of data on the time direction, you should have the chunk more on the time direction. You shouldn't have the chunk on the time direction. If you need to use it on the x and y direction to do the aggregation, you shouldn't have the chunk on that side. So if we can also create a chunk also just on one file. So for example, if we have the longitude with the 40,000 and the latitude on 50,000, we can also say we just want to divide it into 2, for example. And then, so by setting that, you can also set it on the, like, for example, chunk size as 600 mega. So because we just divide it in a 2-way. And of course, you can change that on different direction, different split. And then, for example,
I think, Tina, you should mention what is in this warning box, because this is very important.
Yeah, to access this chunk with 600 mega each, your process will be,
I think the thing you have the chunk, the instruction you give as a chunk, you can divide, but if the native file has very large chunks, so like this NetTDF file, if this is only one big chunk of 2 GB, when you will process one chunk, you select your data, it will still need to load the 2 GB into memory to extract only the data you need. So this is why when you are preparing the data, it's very important to have the chunk that are small enough for people to be able to load only small parts.
So that's why we will have afterwards the ZAR and care chunk, which will be very important because that is already chunked very small, and which is also will be related when we load the file from the stack. That will be shown by the Lorenzo afterwards notebook, the explanation. But that's even for loading the file of the stack, you can also specify this chunk size so that it doesn't crash your PC. So, so this is X-array data set and the data array. So both objects have this chunk function. So we can use it. So once you load file, we can change the chunk, and then make the we can use it to change our data set chunks. Yeah.
Sorry. So does this mean all of the stacks
Yeah.
are already pre-chunked at arbitrary chunk sizes? Because how would I know which chunk size any given stack would have?
For example, the stack, the default one.
Well, we will see it later, I would say, and you will have a better understanding. But what I can tell you is that there are data sets that are coming already chunked, and there are data sets that are not chunked.
Yeah.
In this specific case, the Global LAN service is not providing NetCDF's data set already with the defined chunk. So it's really hard to work. And we will see later why it's also important if you need to select a specific area. Okay, so it's really depend. Then there are other tools that you can use to convert huge data set that are coming. Let's say that you have a really long time series, huge in terms of space dimension, and you need to deal with it. There are specific tools that you can use to re-chunk everything, because it's not that easy if you have a pretty big single image, let's say, okay? So we will see a little bit more later on.
And also with the GeoTIFF, right?
With the
Yeah.
GeoTIFF, the GeoTIFF has basically a encoded chunking that is 512 by 512. But later on, we will see how you can, well, if you are using a stack catalog, how you, or the stack, how you can adjust the predefined chunk to basically adapt to your facility or your needs. So we will see a little bit later.
Yeah, so once you load data, so now, for example, we can like slice so that this is like you select certain part. And then once you select certain part, for example, we can try to play with, say, using this chunk function. So if you, like, you can execute your notebook and see, like, after selecting this, we just selected a test as this LTC knobs. We just select one part of latitude, one part of longitude, and then we execute this test, and then you will see it's a very small portion of it. So we can click here normally, and then you will see this data there. And then we can say we will try to chunk this file with a 600, and so it will just chunk it with the 600 times the 600. And then so all that file that was like a 9.5 megabyte, it will be chunked in like 8 bits of 1.37 megabyte. And then so you will have like 8 chunks. So these 8 chunks, there are namings. So once we will see afterwards about that, this naming will come back. So please try to remember. So you have 0, 1, 2, 3, and then 0, 1. So this part is called 0, 0. And next one is called like 0, 1 or 0, 2, 0, 3. And you have the 1, 0, 2, 1, 3 here. So these operations, you have 8 chunks. I didn't forget anything. So these 8 chunks, we can see it in the visualization. So there's in the Pangeo environment, we use the X-ray and the Dask. But this Dask processing, it's all these workflow, you can visualize it, which is kind of same thing as this OpenEO's, this visualizing this box and thing. It's the same concept. So this test data, we can say test.data.visualize, and you will see what it's doing behind. So you had your original data, and the X-ray said, okay, I chunk it to 8 pieces. Okay. So sometime, like when you are doing your simulation, it's good to do this dot visualize to really think about what exactly it's doing. And this test data, so this test, so this how this will relate with Dask, it will be on the next notebook. But so by applying this chunk function, so basically, so you just same as what Anne just said. So first of all, if you can see here, like first of all, it is collecting all data, and afterwards it's dividing into small pieces. So at this part, if you load too huge data, this is the part where it clashes. So you, with this graph viewing, you see what is basically the bottleneck for your memory usage. So you can, for example, like you try on your notebook, instead of using this 600 here, this chunk 600, you can have different method for chunking. You can use, you can, for example, try to set auto, or you can also try to set -1, or you can also try to put like a size, like a megabytes. And then you can also define latitude and longitude on a different cases. So if you, but I guess if I show each of them right now, I guess I don't have time enough. Yeah. Yeah. And there is one thing which is very important, is this -1 and auto. So I will probably show you that. So you have, if we had the 600, but if we say auto, what it will do is like it will automatically calculate the size of automatically calculate the size of the chunk, which, and then it will set basically one chunk should be about 120 megabyte, and then it will recalculate your size that it fits to this automatic value. And if you, for example, set -1, so I don't see it very well, this one. Maybe it's better that I show you more on this one. Up. So I have LTS. And then I have LTS knob, for example. It's not knob, sorry. Knobs, okay. And then if I say like a chunk, it's better that I show you next to this my example there. Up. Voilà. Sorry, chunk. And then if I say auto here, and then you see like it's set the value by 128. And for example, I can also use this one. What did I do wrong? Chunks. Never do the interactive. Never do the interactive. Maybe. Ah, yes, it's column, yes. Yes, that's it. Yeah. So if you see it, it's a sliced right now. So if you put the -1, it means that you don't do the chunk. And this, you will use it when you do the chunk. Because, for example, if you don't want to chunk the time direction, what you do is like you put -1 on the time direction. And afterwards, if you don't know what kind of size of like a chunk on this way, you put auto. Or like if you say, I want chunk on 100, and the other part, I want it to compute automatically, it will be, you can really play with it to see how it's really chunks the things. Any question? Yes?
So the question about this auto and 128
Yeah.
megabytes.
Yeah.
So where those 128
Yes.
comes from?
So this 108 is coming from Dask's default value. And then if you want to change, so I think it's really like machine dependent. If your PC have like a lot of memory, like I use a machine on HPC, like I have like 128 giga of memory. And my auto, I don't set it as 128. I set it as like 1 giga or something like that. So it really depends on what's the size of your cluster using. And yeah.
But this is, so the user of X-Array specifies her or himself
Yeah.
This value, or it's recognized?
It's the Dask itself, it's setting it as default 128. So if you touch nothing, it's always 128.
So it's actually not auto. So the user have to look at the configuration and set it. It's not that Dask is looking at your configuration.
Dask doesn't look at your cluster configuration, unfortunately. That would be really cool, I think. Yes.
So not so auto.
Yeah, it's not so auto, yeah.
We're spending a lot of time on this question of chunks, what chunks to use.
Yeah.
What's the best? Should it automatically figure it out? I think it's fair to acknowledge this is not a very good user experience.
Yeah, it is, yes.
To
it is.
I think it's important to realize that we've kind of just moved the problem.
Mm.
It used to be we had 1,000 files
Mm.
that we had to process, right, in the old way. And we had to write some loop and go over all 1,000 files. And now we sort of moved that problem. Now we address all of our data as one big unit, but we still have to think about how we split it up.
Mm.
And where I think we need to go as a community is to get to the point where a normal scientist doesn't have to think about any of this stuff, right? So I think we should just be very clear, this is what we have to do today.
Yeah.
And if we learn these tricks and these special recipes, we can do some amazing things and process huge volumes of data. But it's not smooth, you know,
Yeah.
unless you have
Yeah.
mastered a lot of
Yeah.
tricks and
Yeah.
things like that. Right?
I mean, for the people who was doing like MPIs, or I don't know, how many of people did MPI before? Right?
Disaster.
Yeah.
Was a disaster.
Yeah.
I
So,
didn't, just to explain my experience with MPI was a completely disaster. No, because I don't have any background. I'm coming from forestry. I try to imagine a forester that is dealing with the MPI.
Yeah.
So it was bad.
So,
Okay.
yeah. So like, I mean, if people who did know how to program code on MPI, like parallel and so on, this chunk, idea of chunk is so simple because it's same as like parallel thinking. But it's like as Ryan said, it's true that you need some time and you need some experience to just gather it. And definitely this is something. But there are some special trick. But if you master this -1 to drop this chunk for certain calculation, so like if you imagine, like, well, I would maybe better explain it on the task part. But if you know what you are computing, and if you know which direction of data that you have to use at the same time, and if you put -1 on that one, basically you do less mistake, and that goes faster.
One point, I totally agree with you, Ryan, but one point that I would add is that actually that's the reason by which I really love the idea behind the OpenEO. The OpenEO is kind of abstraction, so you don't have to deal with this, all this stuff. Basically, it's much more easy for scientists to process a huge volume of data without getting crazy with all these chunking, and there is a drawback, but I will try to explain you later just at least my vision on this and why we still need Pangeo for some stuff.
But presumably that's just moving the same problem to the server side, right? I mean, this is irreducible.
Yeah.
There's no magic that can make this problem go away.
No.
It's simply what sort of interface
But
the user will see.
yeah.
Yeah.
Stronger hardware.
Yeah.
You have to pay for that.
Yeah. So if we move,
We have one.
yeah. Yeah.
If we can take it.
How would these kinds of errors be viewable by the user? So which kind of error does a user get when he gets the chunking wrong?
You have to wait long time, or your calculation crash.
Or you will get crazy as me. So if you don't,
Yeah.
If the error message makes the user obvious or makes it obvious for the user, yeah, okay, hey, please.
Basically, if your chunk is too huge, your calculation crash. So you can make it smaller by smaller, because if you start from small, your calculation stumps and it's so long. So I would suggest start from big chunk, and if it crash, make it half size, make it learn. If it stumps, then you make it a bit bigger, and if it crash, you make it again smaller.
But I think it's exactly the point when you lose the user.
Yeah.
So if especially the user with scientific background, so that they want to process the data, this is exactly so that goes back and forward.
Yeah.
They don't have time for that. So they maybe a PhD student, yes, but others they just want to process something that doesn't work, then this is a point to leave this and do everything manually yourself. So you cut the data, you do the batch jobs yourself.
Yeah, but that if you know how to cut the data, this setting up chunk is not difficult, because how you cut the data, you put it in the chunk size.
Yes.
It depends as well.
You
what
know,
you have to
so
achieve.
if you know it.
Yes.
So you just need to.
I tried a few years ago this chunking, and this was exactly the point when I left. That's why I'm saying.
Okay.
No,
Okay.
but
But it's and also the Dask is evolving since some years, so there is less bugs comes from the Dask side. So I'm sure, like if you try it again now, it did really made a lot of progress. And what it could be interesting is like also try to use a ZAR format with a chunk, and that's basically go to the next section if we have no other question. No, it's okay. So I mean, so I will just quickly go around about the ZAR part. So if you try to we can save these format whether in like a netcdf or ZAR. But if we save it in ZAR, we can keep this chunk in the file. So we can look at you just need to say to ZAR and then you overwrite as a mode. And then if you look at this ZAR file inside, basically you in the knobs directory, you have this 00, 01, 02, 03, 10, the one that I showed you, this 8 bits. So what it does is basically each chunk, it saves it in a one separate file. So you hear like, oh, new file format, it's complicated. It's not complicated, it's simple as a netcdf. It just make the directory for each data set, and it's just saving the file in there. And because it is saved in a different file set, so that's why when we want to load this data, it won't load again this big bits of 2 giga, but it will load just one file by one file. So that's why it won't crash the memory afterwards. Yes?
Is this then done along all axes? So you have chunks along all axes, and then when reading in, you just concatenate the one you are interested in the whole direction. You know what I mean? In this case, if you save it,
Yeah, I saved it.
then everything's chunked in each direction.
No.
Depends on how you define it.
Depending on how you define the
It's
chunk.
same, okay, it's
So this example is the one which was which I skip. I was on the 600. Yes, this example. So we separated in 8 chunks.
Right.
So if we separate it in chunk, and then it will be saved on 8 chunks. So, but if, for example, if you want to do the time chunk, then you don't separate anymore on the time. It is already saved in this longer thing.
okay.
So that's when afterwards, when you want to process it, it's already in a good chunk. And then what I should kind of speed up fast, because it's 4:15 and you will have a coffee afterwards. And so these chunks, when you think about, like if your file with a I'm coming from more like on a model side, and then we often have a netcdf file. For example, for today's like January's netcdf file, February's netcdf file, March netcdf file, you have like different netcdf files. So basically, these different 10 netcdf files, it's same as chunk, right? The netcdf file is already chunked. So we can also load these netcdf file, separate netcdf file, as one file. That where comes the care chunk. So so with using a care chunk, we have like a different, for example, this is an example of some netcdf file we have on the cloud. And then these netcdf file, we can use a care chunk and then basically concatenate it, and then we can see it as just one data set. So I skip this part because I'm getting a bit slow. So I can show you not this one. Not this one again. That's it. So there was this here, it's 36 file. It's coming from these 36 files. We can use a care chunk, and have this 36 netcd file as if it was one ZAR file. So we don't, with the process that I just showed before, you read the netcd file, and you crash it as ZAR file, so that means you write twice. By using this care chunk, we can just collect the metadata of each netcd file. Care chunk will combine this metadata file. We will just save this metadata file somewhere, and then we can use this bunch of netcd as if it is already a chunked ZAR files.
Just for the GIS people, if you know, the VRT approach is the same.
I was just about to ask.
Yeah. More or less like a.
Yeah. So this is a process, like maybe you can afterwards copy and paste and try to, if you use a netcd file, you can try to copy and paste and apply that on your 1,000 or 2,000 or 3,000 netcd file, because I use it for my yearly file. One year I have hourly. So you can imagine, like, I have 8,000 files to load OpenMF dataset, which takes ages and ages. And CareChunk basically changed my life. Thank you, CareChunk. And so I have my dataset. And then once you make this CareChunk file, so which is a JSON file, for example, this notebook that you can try, you need to open this JSON file as a ZAR. Right now, there's a new development XRA that they are trying to open it much more simple way. That's so that it should be a simpler, I guess, very soon. And these files, you can also input it in a one catalog file in the intake. And for the user size, basically, if you have the path to the catalog, you just need this one line of code, this cat.lts.toDask. Just one line of this code, you have this 36 file loaded, chunked already in the XRA. So that way, when you do this parallel processing, for the user side, you just need one line, and then for the application side, it is already chunked. So which kind of links very well with the stack example afterwards that you will see, because stack also you have a lot of chunk from the beginning, and the user, you just need a several line to load the file. So satellite data, we have stack. For the model data or whatever, a lot of netcd data, we now have a solution, care chunk and intake. With that, we can really have that already chunked file loading really easily.
Excuse me.
Yes.
This care chunk works only with ZARs, or
Care chunk works with netcd. There's also Grib. What else care chunk works? Ryan.
Basically everything. You know, basically every file array or raster file format, we've discovered we can map it to the ZAR data model and apply this sort of layer over it.
Using a care chunk. Yeah.
Do the coordinates have to be aligned, or do the coordinates have to be aligned?
Yeah. Yeah. Yes. Yeah. That's it. Yeah.
So if you try just to, I don't know, if you are used to the Sentinel-2 data coming out of ESA, no way.
So
Yeah.
it means if we have a hole in the data, it's not filled with nulls, or like it's not like a union of coordinates and then where it's missing it's none, or just crashes.
How does your file is made?
It's
No,
very
but
low level. It just operates on the bytes. It doesn't really know anything about coordinates. So you stick together arrays if they're the same shape and the same data type. And it's not aware of space or geometry or CRS or any of that. So it's up to you to use it.
But maybe his question is, if I didn't get wrong, is that he has, let's say, two tiles that are far away. If the system is able to create just one huge cube with all the nulls that are needed to put the two tiles in one cube.
But it doesn't.
Not really.
Exactly.
No.
Yeah, because this is like usually, like taking bounding box and then from that to make.
Okay.
Is there any more question around chunking, or shall I go on to Dask? Okay.
Just the still the underlying
Yeah.
formatting of the files as you've done it
Yeah.
initially
Yeah.
is still crucial if you want to parallelize later. It's not
Yeah.
by rechunking or doing this ZAR that you will recreate, because at the end of the day, the same structure will still be there. And if you've done it, or if it happened to be in the wrong chunking
Yeah.
of time or the, XY dimension, you still stuck with that problem later on if you want to parallelize. If you should redo the whole thing, it's not by doing this.
Yes. Yes. For example, with this cat chunk, and afterwards, if what you want to do is, if this side, if it's not, this part is not chunked at all, but you just want to chunk on this way, right?
Yeah, I mean,
Yeah.
when it's wrong,
Yeah.
say in the very beginning,
Yeah, yeah.
it will
Then it's
stay wrong at the very
There-
end.
there- there is-
That's why it's so important.
But the thing is, in case you're using netcdf, and if you have HDF file behind, the netcdf file, in fact, the file itself is a one file, but netcdf file, HDF file is chunked.
If they have done it and not
If they
change
have
the
done
chunk.
Yeah. So it's,
You have always the same.
yeah. But the thing is, like, in one, before cat chunk, just with netcdf file, it was not possible to recognize the chunk in the HDF file. But with this cat chunk, even though the file is one file, but it now can recognize the chunk in the file. So if it is a time, and then if it is a spatial, then you have a chunk on both sides. And if you have a chunk on both sides, X and Y and time, basically you just need to regroup it. So you don't crash because of the too much memory. You see what I mean? You can make a group of chunk there. Making a group of chunk, it's not a problem.
You still have the same problem if your data is not chunked properly. As a
If you want- at the
provider
end,
side,
you want to do
it's
one
not-
pixel at a full time series, and it
Yeah.
has been chunked already in the XY, and then the problem.
You can
Yes.
group it.
no, you can group it, but you can group.
But
Grouping is
doesn't
fine,
touch the
but you
memory.
cannot go lower.
I would say that specifically for the data that the Earth observation is more in, I would say that there is really need from the data provider to provide data that are already chunked.
Chunked, yes.
These example, at least the long-term statistic, it was based on a data set that wasn't at all chunked. It's, I would say, a small data set, so it wasn't a real problem. But if you have to deal with bigger data, let's say higher resolution, it's a disaster. Okay, so my message would be that the data provider should provide chunked data set on the original side. Then the user can recombine the chunk according to his needs. You were mentioning a time series. I would say that if you have to pixel base do a time series analysis, most probably the best would be to rearrange the time dimension, as most probably you will arrive with one single chunk per each single time, and most probably you will have to rechunk to have just one chunk along the time dimension to speed up. We have Ryan that is
Well, this is just such a common use case, right? We have a data cube,
right.
and we have different ways we want to analyze it. And some organizations support one way and some support another. It's useful. One of the teams we work with came up with a pasta analogy. Right? You can have lasagna,
Yeah.
right? That's your typical stack of maps. You can have spaghetti, right? Time series analysis, each point you need to pull out, or you can have ravioli, right? More isotropic
Ravioli, yeah.
chunks that are not optimized for any one particular, but
Yeah.
are
Can stack
okay
it.
for everything, right? And you know, you have to make
This is ravioli, right?
yeah, exactly.
Yeah.
And so you know, you can.
Stack it.
Unfortunately, there's no perfect.
No, but
thing that
that I
supports
totally agree, but
No,
I think with the re-chunking, it might give the impression to some users that it's solved. But at the end of the day,
At the end of the day, some bytes are close together on the disk, and some are far apart.
Yeah. I mean, but in case of the good point of Labioli is like you can group it. It won't crash the memory. So if you can, because if you already have this lasagna, it may crash your memory, so you can't do anything. So the good thing of Labioli is, so what Lorenzo is saying is that a data provider should provide a Labioli so that people can group it so that at least you can calculate something. But not too small Labioli, but have a certain size so that it's, because grouping also takes some time, but better than crashing the memory. Yeah. Okay. So can I go to the task part or, yeah. So,
In 4 minutes.
yeah.
Stuff, but you
So I have to talk Dask in 4 minutes now because, but if you know chunking, then Dask is easy. Okay, so Dask, you have another notebook for the scaling with Dask, and so that's this notebook here. So I will go very fast because anyway, we will see it later on your notebook. Yeah. So Dask. So we parallelize Dask. What is Dask? So it's Dask, it parallelize. Okay, and then you can use a Dask on, so Dask, the Dask array inside, it's like a Labioli of NumPy array, right? And then, so basically when we want to say do the compute, Dask will analyze what kind of gathering you need to do and what are kind of computing that need to do. And then it will schedule for the each Dask workers. You do this, you do that, you do that. Not like MPI time that you have to write and schedule yourself. It's Dask which will magically kind of try to make the graph and then do the compute. And there is some important aspects like dot compute, dot load, dot persist that will come back to Lorenzo's notebook, so I skip. So like you have, when you start Dask cluster, it will start the cluster, and then the cluster will have some workers that I will show later. And then this is I can skip. So let's see how it looks. Okay. So in your notebook, what you should do is you just should copy and paste this stuff in your notebook that you have actually. And then if you just do that, what you see is like there is some sort of the dashboard which starts. So this is something important. So you would, this is something called the Dask dashboard. And when the Dask compute, you can monitor what it is doing by using this little nice icon here, this Dask dashboard. So I will show the Dask dashboard things once we are, and then. So basically what we need to do is like you need to copy and paste, unfortunately. Yeah.
So just
Voilà.
make sure you put your username.
Yeah, yes, username here. No, don't put Tiyodaka, yeah. And then so that it's all explained, so you can try it by yourself. And then, so for example, we can click like cluster map. I like cluster map because it's cute. You see, you have this is your workers. You see that you have 4 workers, right? And then what else, which is nice, is like graph. So you can click graph. And then you see some graph, like it explains you what it does open data set, or it does something, and so on. And then you can also click the progress, and then you will see what it is doing right now, how many progress that, what kind of a process that is left, and so on. And you can also click worker memory, and then you know you're not crashing memory. So you have 8 giga in total, which worker is using how much memory right now, and so on. So this, you can close it so that we have a bit bigger place. So with this, basically, if your calculation, while your calculation is running, you can monitor it and see if it's stuck because you put too much memory, or it's swamped because you cut your chunk too small. So you can guess something to have good size. So what I will show you is this catalog that we made just before. We load the data with a catalog. And then let's say I want to just select some small part, and then I want to do the mean. And I don't know why I want to do it. I forgot. Yes.
Just a very quick question.
Yeah.
But is it possible to get the read from how many bytes you have per worker and then maybe optimize this?
Yeah,
in
sure.
a small sample?
Yeah.
So, okay.
So you have a lot of possibility. Worker memory, there was RAM memory. I think there was I/O also somewhere. I don't bandwidth. So you can see also bandwidth. That you So they click everything and try to have fun. You know, while coffee time or this afternoon or until the end. So this is the yeah. So So a task, you can also optimize the task, which is a bit more complicated thing. But so if you see that once you define your calculation, for example, this one, so if you can look at this part, you say, I want to select one part and I want to do the mean. And then show me if you just click that one, the data, and then you just can see what task will do. Here, we know that task will do like 7 layers. But if you want to go further and optimize this kind of thing, you can also just copy and paste this one, and then you can see like you can optimize this graph, and then you can, for example, visualize it to see, and I hope it doesn't crash, yes, to see like what, you see how this data set is doing. It's a data set. It is trying to do the mean, and then it's doing to combine the mean because you have different chunks. So it is working on different chunks and doing the mean of the graph of the group of the mean, and so it goes combining the mean. So that's what you can see. And yes. So for example, if we do this if we do the time as -1, and then the visual graph, it changes because we already combined different ravioli as one before we start to compute, for example. And then this client wants, what we can do right now is to see, so this was an example about Dask local cluster. So if you run the same example in your PC, you're using your Dask on your local cluster. So Dask can run different workers on your local PC, so you can use different, because now your PC is many cores. So you can make use of your many cores using this Dask, so which sure will help your runs. I mean, you don't have to use the HPC or cloud to do, if it's for certain size, you can really make use of your PC. That's really good thing of this Pangeo environment. You can test it on your PC until certain size, thanks to your cores and memory and so on. Okay, so now I'm going to the Dask gateway. What is Dask gateway? So Dask gateway is, well, what is Dask gateway? So it's a kind of gateway, right? So right now we used example with your local cluster. What we will do is we will use a Kubernetes cloud cluster on the EOSC that is setted, like if you say, I want to use the Dask on your cloud, it will say, okay, I will run your workers for you, so your notebook can be connected to cloud, which is side by side, and then you can offload your calculation to this cloud, which is just next to your your notebook on the cloud. Yeah, and we will show again that example afterwards, but it's very simple to try it on this EOSC thing. You just need to, click and click. And then you say, I say the gateway new cluster, I make a cluster, and normally it should run, and then, of course, okay?
Just to see how much you ask.
So
you specify the size of your worker.
Yeah.
It's exactly as before, but you have to specify how many workers.
So in this example, I asked for 4 workers. And then, so you have, we have 8 giga. And then afterwards, we can click this dashboard. And then we can copy and paste this dashboard to the side, which is not automatic, which is very, that's something we need to work on, but anyway. And then we can see how, so we can do exactly the same thing. But one thing, though, we can do exactly the same thing, but if we want to go more like a bigger calculation, we just need to ask more workers, more memory, and then it will run in parallel. Yes? Close it. Okay, I should stop talking. Okay. So what I want to say just before is stopping is, what did I wanted to say? I knew it, but I forgot. So when you do this task in the task gateway, you need to think that is not the same machine that you're using as notebook. So your file, which is on your local, the cluster next doesn't know it. You see, it's like I start my task, I have my notebook, I offload it to Lorenzo's PC. Lorenzo's PC doesn't know what file I have in locally. So if you are treating the data on the cloud, it's not a problem because cloud is, you can connect with internet. So if you are, for example, using the data on the stack that is on the cloud, if we are checking data right now, the chunk catalog, I put it on internet, yes, this worker can treat, but worker will not know the netcd file you just saved on your notebook. That's something you really need to understand when you use the task gateway. That's
Okay, now,
Okay.
as you are talking from 0 to hero in Pangeo and task stuff, I would say that we can close it. I will try to unterrify you from all these later on with the presentation that we will have to demonstrate how, in a practical way, you can use all this stuff.
Is about how to exploit data with OpenEO and actually also with Pangeo, Xarray, and Task. So what we will do now is to go through the same exercise in different ways, basically, with classic OpenEO on the server, OpenEO on the client, and the same workflow again expressed with Xarray and Task directly. The last part will be done by Lorenzo, and I will talk you through this. This part was supposed to given to you by Michele Klaus. Shout out to him. He prepared all of this material here together with Lorenzo then for the Xarray Task part. Unfortunately, he got sick, so I am stepping in for him. My Python and Xarray and Jupyter skills are a little bit rusty because I don't get so much time anymore to do actual data processing, but I hope I will still be able to carry you through this code. And I had a fun time on the train here to setting up my environment on my computer at least, and it's running, so I'm already proud of that. So let's see how it goes. So again, you should be able to use the Jupyter environment provided already earlier. The notebook that we are looking at now is the notebook that is called Data Exploitability OpenEO IPython notebook here. What we work here is we will take one of the lectures or of the training materials from the online course that we have been talking about earlier, the Cubes and Cloud course that we currently develop, and use that as an example, this material here of how to do this processing. This is a use case based in the hydrological domain, which allows us to look into the relationship between snow cover, and when snow cover disappears, usually the snow has to go somewhere. This is a melting process which produces runoff, so water that is going down the mountain somewhere. And we will see how we can express such a relationship with OpenEO, looking into mapping snow cover based on the NDSI and some masking and some other tasks, and compare it also to runoff data from some gorging station that we put in here for you. That's basically the background. So what you see below here are actually these two curl commands which allow you to download two different notebooks. The first one here is called 31 Data Processing OpenEO Platform. This is the classic OpenEO workflow where everything is happening on the server side, so to say. And then the second notebook is the data processing stack that is using a new thing that we have introduced in OpenEO this year actually only, which is called client-side processing, where all the processing is happening on your own machine. What it does in the background is actually fairly close to what you have seen earlier today. It will set up a mini Dask cluster basically on your local machine, and it will use one of the different OpenEO implementations that are out there, which is based on Xarray and Dask. So all the processes that are defined in OpenEO you've seen before in the those of you who have been here in the morning session at least have seen before that OpenEO has a large number of predefined processes, and one set of these implementations is available also in Xarray and Dask in the corresponding repository in our GitHub repo. And these are the processes that are used also in the client-side version here. This is different, for example, than the processors that we have seen before from Jerome when he presented his part, which is running on a completely different processing engine. Again, the nice thing with OpenEO is that we are completely independent of the infrastructure where things are running, basically. And today we will see that here on this example with the client-side processing. Okay.
That's because we haven't installed curl.
Okay, I see. So just use wget then to download this file.
So wget and the HTTP address you have, and then it should download. Any problem? Just raise your hand.
Okay, so
yes, because it will take the name to send you.
just do something like this and then minus output, right?
No, minus output, just wget like this.
And then comma, you can take out the quote. On the other side also, in the end,
You have a quote.
quote at the end.
Yeah, I don't know why it's not jumping to the end there. Okay.
It's a matter of that we don't have curl installed in the
Okay.
Yeah, it's fine with code because we don't have any environment variable or whatever. We quote or without.
Okay, this was a misunderstanding. Anyways, you should be able to get this notebook in this way. Once you got the notebook, you should exactly all of the. Whenever you go to a command line executable on the notebook, you have to put this exclamation mark in the beginning. That's basically something which happens directly. This would be the same as when you go and open a terminal and then just write it here directly, basically. This is what you achieve from the notebook by putting the exclamation mark in front of there. Okay, good. Then the next thing is we can look a little bit into these notebooks and how they actually look like. So when we want to do the data processing, we saw already some examples in the first session, in the part 2 session on OpenEO. This allows us to load some satellite collection, specify the extent in space, time, and features. Features in our case might be the bands of our multispectral satellite mission. Then we do some processing in order to retrieve information on snow cover, so we will do that, aggregate information in data cubes, and then also have a look at the results. We are doing this here always with the Python client. It's maybe also worthy to note that in OpenEO you're not limited to work with Python. If for some reason you prefer to work with R, a lot of this stuff can be done with R as well. The only thing that we currently don't have in R is the client-side processing. That is only available in Python. But in terms of developing the code and running OpenEO on the server side, you can do everything also with R and actually also with JavaScript. So there are 3 fully developed clients right now. The JavaScript version is the one that's also behind the web version that you have seen in earlier parts. Okay. So the first thing is we install some of the libraries that we need here and import all of them. OpenEO again is available through pip, so you can just do pip install OpenEO. In this case, it has already been done in the environment for you, so you don't need to do that. And then there are just a few other things that most of the part that we extra import here is actually just for the visualization part. All the processing, you just need the plain OpenEO library. And then, as you have seen before, we connect to OpenEO.cloud, we authenticate, and once we have done this successfully, we should be able to see with something like this, just to check if the login worked, that it's the right user. So I logged in here with my own user, so I can see that it worked perfectly fine. You should there see either the EGI account that you have registered beforehand, or the one that you get handed out on the small snippet that we got here. And then we go into the actual analysis already. So the first thing that we want to define is the area of our interest. In this case, we look into one hydrological basement, a catchment, that is situated in the Alps in this example. This file has been preloaded for you as well on the in the repository. So if you want to check, you can find this in the data folder here. There's the additional files basically, and that is what this path here is referring to. That is defined in the GeoJSON format, which is one of the standard formats that we use in OpenEO to define all kinds of vector information. So we heavily lean on GeoJSON there. Then we can do things that you have already seen before. Just I will skip over that. Just list the capabilities of the backend that you're connected with, and check out some specific collections that you can use there. What we can then do is to get a bounding box based on the extent of the file that we have just uploaded and loaded basically. So all we do here is get the minimum bounding box around this file, so that we work only in the area of interest. This is again just to reduce the amount of data that we work. We always try to follow this paradigm that you only work on the pixels that you actually need, so to reduce the amount of data that you touch, which next to the chunking is another very important thing to always consider, to not load more data than you actually need, because this will just take much more time and cost. So always consider to make the amount of space and time that you query as small as possible. In the next box, we just parameterize all of this information so that we can feed it into our data loading call, which is the load collection that you have seen before. Again, we use Sentinel-2, the atmospherically corrected level 2A data. We take the bounding box from that we have just defined before. We specify a temporal extent here, some data between February and June in 2022, and the bands that we need. We want to calculate an NDSI here, the normalized difference snow index. For this, we are mostly interested in our, I think the band 3 is the green band, and the band 11 is a shortwave infrared band. These are the two sources of information that we need to calculate the NDSI. So we only load those bands because we don't need all the other bands for this exercise. Again, with the scope to reduce data. And the next is we also don't want to deal with basically completely cloudy data, so we exclude data sets which have a cloud cover of 90% or more, because they're basically useless for us, again, with the scope of only using data that has some valid information inside there. And from that, we put all of this information into our load collection call, which will give us the actual data set. When I say which will give us the actual data set, always remember that in OpenEO, what you do when you write this code is not doing directly execution of code. What you do is in the background to generate this process graph. This is why all these boxes here will execute very fast when you do that in your notebook, because all they do is generate a little bit of JSON text, basically, in all of these cases. So right now, when you do load collection, or in the next example here, we will actually calculate our NDSI based on the green and shortwave infrared band. Then when we write all of these mathematical operators here, no calculation is happening. All we do is defining what we want to do, and this will be translated into the process graph that we generate, basically. The only nice thing that we have been spending a lot of time on, mostly actually colleagues from Girone at Vito have developed the Python client, make that feel as much as writing normal Python code as possible. So you're not sitting here and create JSON object with node number something and put in some operator there, but you just write plus and then it generates the appropriate JSON code that defines that for you, basically. Then we continue. Usually in these cases, when you use some index-based method like this, you do some kind of thresholding. So in our case, for example, we say we are pretty confident that there is snow when the NDSI value is above 0.42. NDSI is a normalized index, so the value range goes from -1 to +1. Yeah, we just say if the value is above 0.42, then we are quite sure that there's snow. You see very similar things with the NDVI all the time when you, for example, want to identify vegetated areas. Works the same way, basically. The next thing is then to have a look at our, to remove the effects from clouds. For this, we can use another band that is available in our, whoopsie. What did I do here? I just went into the edit mode. How can I get out of this again? Maybe just execute it. Okay. See, that is why I'm a Jupyter newbie, basically. I never use it. So this is just giving us all of the scene classification is basically a part of the pre-processing when you generate your atmospheric corrected data. And has all these labels that tells you about the validity of the pixels that you have. So it says there are no data pixels where the registration in the sensor has not worked. There are defective areas of shadows, either from objects in the scene or from the clouds, vegetation or non-vegetation, water or non-water bodies, and also probability of clouds of different types, medium thickness, high thickness, very thin, more kind of haze, cirrus, or presence of snow and ice. This information we only use in order to find the areas which are most likely not useful for us. And we can do a second load collection here in order to get our scene classification out of the data set. So all we change is basically with respect to the previous request, the band that we actually request. Before we asked for band 3 and 11. Now we are asking for the band that is labeled SCL. And then on this band we apply some, this time it's not thresholding, we are basically just selecting the values that we are interested in, the ones that represent the presence of cloud or cloud shadow, basically. When you look into the legend here, number 3, which is this one here, is the cloud shadow, and number 8 and number 9 are the medium and high clouds. Okay, and then we continue all of our road here in order to apply the cloud mask. So the next thing is that we take the snow map that we have generated before. So the snow map is what came out as the thresholding from the NDSI, and apply there the mask so that all the pixels which are not valid based on what we have specified here and put them out. We put them onto a value which is 2. 2 is a good value in this case because 2 is outside the range of what the NDSI is defined with. So we can quickly see that this is a wrong value. And then the other two values are 0 and 1. Sorry, 0 and 1 is actually, when we did this operation, that was basically a Boolean type of operation. Our data set was already converted into zeros and ones. And then we add the 2 here just as a marker for the clouds. My mistake. So this is basically like a classified map which has 3 classes: no snow, snow, and cloud. Then we can crop this extent to our catchment, the polygon file that we have uploaded already beforehand. Here we can use a different algorithm, which is mask polygon, which allows us basically to define a mask not based on some threshold or some value, or but just saying only use the pixels which are inside our polygon. That is what we do with the mask polygon operator. And in this case, we then, after we download here one example, we can actually see that after this we have only the cropped extent of the file that we uploaded in the very beginning, which was basically here. I didn't run all this notebook, so I see that this part is missing. And then we can continue with our work here. I will now switch over to the other notebook, the one that is on the stack part. The stack notebook looks very similar. The main differences, if we go back now, are when we start, we have to import some different libraries. The first part is we upgrade our OpenEO instance to include the local processing, which means that we also use the extension. This is basically an extension of OpenEO, this client-side processing. This allows us to do the processing locally. In order to do that, we need to copy some more Git repositories and compile them, and install based on them our client-side OpenEO processes task here. So this is basically the setup of this mini Dask cluster, which I mentioned earlier. That is the only difference in terms of the setup of the libraries. And when we then start working with it, we have this .local as the extension that we have added here with the local processing. And we have a different type of connection now. We have had the connection that we used here to connect through the URL to a cloud service. When we work locally, we don't need to connect anymore through a specific URL. Now we are connecting actually to a path. We are connecting, in this case, to our working directory of our notebook here by just using the // basically, which means that we are able to work with data sets that are in the directory where we currently are. And we are also able to pull in other data sets that we might be interested in. So in this first example, we were using a collection that was available in OpenEO platform in this case, which was the Sentinel-2A collection. In this example, we will use the same type of data, but not coming from OpenEO platform, but from the Microsoft Planetary Compute. What we do here is we specify now not the URL to our cloud processing service, but just to our cloud data, the data that has been defined with stack. Here we have an example of an online available stack catalog, which is not only a metadata catalog, but also hosts the actual data, which allows us to directly load it into our processing. In this case, we have to use a slightly different loading function. So now we are using on our local machine our load stack. And the main difference to the load collection that we have seen before is that instead of defining here a link to a collection data set that we have defined here, we put the URL to the remote service from where we put the data. So this is just this very small part which is different. And then all the rest is basically the same. We again put a filter on the types of bands that we want to load, and the properties. The properties we can put again the cloud cover, for example. We can also specify in these properties that please only use this is now the power of Stack. Actually, we can use all of this metadata information to filter our data already and use all of the different variables that we have there to make sure that we get only things that are interesting for us. So we can say we have the cloud cover limited to 75%. We also can say we only want data that come from one specific tile in the MGIS grid, for example, in order to do not have to deal with any kind of strange overlaps between different, make sure that they all have the same projection and so on. So we specify in this case, we just use this tile 32 TPS, which happens to be the tile which is over at Bolzano where we work. And then we can actually run that. So let me quickly just make sure that I load everything up here. We load our catchment, our metadata, everything is in memory. Here's again the same area as before. And then we can get our bounding box and so on. Now we can load the data using this load stack. This is what all of you have to do if you want to get to the data now. I will quickly, so when you execute this cell, then you're basically connecting to planetary compute. Right now, when you do this connection, all you do is not the actual data download right now. It's kind of just a data query to get what information is there based on the filtering that we have included in our properties. The actual download will only happen once you actually trigger some processing. Right now, it kind of just creates a list of the relevant assets that are in this catalog for you, basically. Since we are client-side processing, this is we can also actually use the data that we have locally available. So what I'm doing here is I'm referencing directly to netcdf files. Yes?
Would you tell me if the data were not available?
It would tell you some kind of error, probably, yes.
So I would already at this stage get a warning if I would request something that later could not work because I'm asking something outside the repository.
I'm not 100% sure about this, actually. I have to clarify that. It would definitely be good that there is some kind of message about this. Okay, so in this case, I have done this exercise already yesterday when learning how to teach it to you, basically. And then based on this, I was able to get the data already, and I have these two netcdf files here. This is for you also to see if you have your own data sets that you already have and you want to bring them into your processing with this client-side processing, you can easily do this. In the end, you're just loading an X-array, a netcdf file into X-array, much like what we have seen in the previous presentations here. So I just load these two data sets, and that is instant because they are locally. There's no querying happening in this case because they have already been defined. And then I can go again with my processing. Now, this part is exactly the same as before. The only difference now that I execute all the cells is that you actually see after every block the graph that has been created from it, just for you to understand that a little bit more, what's actually going on here. So in this line, what we did is, for example, we combined our two different data sets into one data cube by using the merge cube operator so that we have them in one set available. Which we find here in our graph again with the two cubes. When you check in detail, you can see where these different cubes came from, basically in our processing. And then we do all of the processing again, the filtering, the thresholding based on the NDSI, as said earlier, which is happening here with the reduce dimension part. So here is the actual calculation. So this is how the formula of the NDVI translates into a graph. You will find here all the arrayment, add, subtract, divide, and so on. This kind of work is what the Python library does for you, basically. and then we can do the cloud masking and so on and so on, and arrive again at our cropped map. We can continue then and do some more interesting stuff. We can calculate some statistics on our catchment. We can also make sure that other data sets that are after all the filtering and so on still too cloud covered get moved out of there, and in this way see what's happening, how this improves. Here you can also see how our data set looks like, and now probably jumped over some cells, and because of this something is missing in my memory. Never mind that. We can calculate all of our time series statistics that we have defined here, and finally plot our time series. For example, here we look into the percentage of clouds and the threshold. So for each pixel, what we're looking at here is the value of our cloud mask and how many of these cloud masked pixels are in the area of interest, so inside the polygon. Basically, this is what we are doing here, and we only want to have the images where we have enough information in there, so the images where there's enough coverage, basically. Here.
At which point did you actually get data and execute something now? Because you said up to there it was all graphs.
Every time when you have every time when you have either an execute or a compute. Yes, sorry, because I was looking at the time and that was all right.
Go ahead. Because I didn't get an error and I still get graphs here, so I thought.
Yeah, I jumped over some cells. That's why to save time, and that's why this got messed up here now. But
You have another question.
yes.
I have a next question about the data retrieval. They are all get from object storage. Metadata is get from the server itself, but the content, the big part of the data, is on the object storage.
This usually is the case with the stack-based catalogs. When you do this kind of load stack, then yes. When you work with your own backend, then object store is an option that you can have in your implementation, but it's not a necessity. In our case, for example, in Europe, we don't use an object store to store the data. But when you work with this client-side processing and want to pull the data from an online catalog, then this data has to be online available, and then it's usually an object store. But it's either usually a cloud-optimized GeoTIFF or a ZAR file, which most of the catalogs that are currently providing information through Stack are based on, basically. Okay, and then we get here once our time series with all the data sets without the filtered data set, and then we get our cleaned up time series, basically. And then we can also look and compare this to actual data of discharge, which is again in this data folder that I've shown you earlier, for one gorging station at the lower part of the catchment. And then we can nicely see how the reduction, the snow cover area in wintertime is fairly constant, usually in our region in the months February, March. April is when everything is frozen. That means the snow cover is there and stays there. Most of the snow comes like from December to January, February, and then this is more or less the extent that you have. And then towards spring in April, usually things start to change. Melting processes come in, which means the reduction of area that is white in your scene basically goes slower. Where does the water go? It flows down the rivers. This is why you can see how the reduction of snow cover area directly correlates to the increase of discharge that you can measure at the gorging station, basically. And here you can clearly see that there's some point of saturation. At some point, all the snow has been melted, and at this point, there's no snow, and also the level of discharge is then only based on the melt of permanent ice, for example, which is not so permanent anymore. And glaciers basically is the only source of water that you then have once the snow has been melted away, which is typically sometime in July, August, when you hit this point, and then from there until it starts snowing again in October, November, the only source of water is that. Yes?
Do you know why there is no data point between May and mid-June?
That is probably mostly also a period of spring, which is usually a period of not so nice weather, rain and so on, which means that there's a lot of clouds. This is a period of unstable weather, which means with our filtering of here you can actually see that. So these are the pixels which are highly cloud covered, where the aggregation of good pixels in our polygon has not been very high, basically. So these have all been expelled. Here you can see that for the whole time series, a lot of images. Some have been already filtered out directly when we said we only accept cloud cover below 75%, and some have been filtered out later because accumulatively over the whole area there was still not enough information, and then we threw them out as well and then that's why we have this strong reduction in the amount of available images for this time. This gives to the next lecture, which is based on SAR data when you want to cover this time of the year, because snow melting process is also something which you can nicely see with radar data, but it's a topic for another day. Okay, I think I'm going to stop here just to give you a little bit of a view on how this processing with OpenEO works. You could see that the client-side processing and the server-side processing is mostly the same. The only thing that changes is in the very beginning where you connect to the URL, either to a cloud service or to your local disk space, basically, and how you load the data. Yes?
How big the data can be from the local?
This depends on the size of your machine. If you have a very powerful workstation, a client, again, can be another server. So I did this now on my computer. Your client can be a very powerful machine in itself again. So it really depends. If you have a very nice modern machine with a 32-core processor and 128 gigabytes of RAM, then you can already do quite a lot of things. If you have a more portable business-like notebook with 8 gigabytes of RAM and 4 cores, then you can do less. So it depends on the size of your machine. But
when we are inputting the data, it's like our credits will be calculated or not?
in this example, you have zero cost on your end, courtesy of Microsoft, because so far they're not charging you for accessing this planetary compute and pulling this data. In the other case, in this example, in this example, you are actually consuming your cloud credits. Me, while testing this, actually yesterday I was completely depleting my early access account for OpenEO platform that I used, and thanks to Jerome, I now got elevated again to the developers level so that I can do this kind of testing. So that's actually also one very important point. It's a good question to this end. That's why the client-side processing is actually valuable, because here you can really test, develop your workflow. As long as you stick to standardized OpenEO processes, you will be sure that you're also able to execute it in a cloud environment, and then you don't have any problems, and you do not have the clock ticking, the cost ticking, other than your own electricity bill, basically. When you do this experimental phase already on the platform, then it means that you consume cloud resources all the time, which might, of course, quickly then lead to a scenario where you have to buy more credits or something like this. So I think the recommended way of action here is to first develop an initial workflow here as far as possible, and then bring it into a cloud service like OpenEO.cloud, OpenEO platform, or CDSE, the Kubernetes data space ecosystem. Yes?
So what are we actually paying for? It's the infrastructure and running on the server, but also obtaining the data, right? So depending on the backend we use.
Well, I think Right now, all the cost is related to the consumed compute resources. But correct me if I'm wrong, but the cost model that we have now with these virtual credits is based on that. Basically, every provider has slightly different metrics. So what we introduced in OpenEO platform in this federation is a kind of, we call it virtual credits, which is a standardized system which you spend. How this actually correlates to the actual resources is a little bit different from cloud provider to cloud provider. There again, other things like how well optimized the backends are will also yield different types of costs. In a very unoptimized backend, it might be very expensive to do the data processing. We spend a lot of resources. Maybe you have the wrong type of chunking like before. Most of you will see this when you've worked with Google Earth Engine. Very often when you do code that goes along the time axis, you run into this that your query doesn't terminate because it has a just hit the runtime max basically that is allowed there, the cap, and that is basically because in most cases the chunking is not optimized for time, and depending on all of these little things, the costs are slightly different.
I mean, it's just because the interface to obtaining the actual satellite images is awesome. I mean, it's been really bothersome before to actually find areas of interest. So you could actually decouple this and download with your software solution and then run the calculations locally.
Exactly, that's exactly what you do here. In this case, if you find a catalog that has the data set that you want with stack defined, like in this case the planetary compute, then you can do this. You can also do a hybrid approach where you can use standard OpenEO from OpenEO.cloud to just download a scene in the very beginning. So you do a very simple process graph, load collection, save result with just a bounding box in there, and then download the content of this, because with respect to planetary compute, there's quite a lot of very well curated data in OpenEO platform now. There are around 65 petabytes of data right now available already. Having all of the standard data sets. There's even links to commercial data. You have to buy the commercial data separate, but you can get it with the same way of accessing the data. So on the Eurodata Cube, you have the whole planet data access, Pleiades, many QuickBird, whatever. Daniel knows best, but you have a lot of commercial data sets available. If you have a license to use them, Synergize, soon Planet, can make them available to you. You can stack them then just like this basically, and then continue with client-side processing if you want to experiment with them. That's a lot how we work now too, and always with the goal to make this whole data access part. This is actually where also our people, the researchers in our institute, lose most of the time. All the young people, they come in and then they spend weeks and months to just organize their data collection. And that's exactly what you get rid of here when you have this kind of way done. Yes, Ryan?
Can you just clarify what, like, say you're just using this to find an area of interest from a stack catalog. Can you clarify what the OpenEO part is doing here compared to other stack tools that can query a stack catalog and, you know, like align the data?
No, with respect to Stack, that's the same. There's not. I mean, that's why we rely on Stack and have been also instrumental to the development of Stack, because these are basically the same people who have contributed to defining these two specifications. And on this part, on the data access part, you can do the same also just with any other Stack client. The difference here is then the link to the standardized processing and being able to easily scale it out, because once you write this code, you can execute this in all the different data centers that have OpenEO available. This is admittedly right now a limited number. There are around 12 processing centers, more or less, that I'm aware of that serve this. Most of them here in Europe, indeed. Also something because OpenEO is mainly coming from Europe, because it has been initially come through the European funding of Horizon 2020. Basically, that's why most of it is here right now.
Just one on this. There are some data specifically from the services of Copernicus that are not already having the stack catalog. So answering to your question, there is a nice notebook on which which I demonstrate exactly this approach, by which I use the OpenEO to connect to the repository of the services, of the data with the services, and basically using the OpenEO to select a specific area and collect on the local machine. I can
Even though there is no stack catalog.
Exactly.
I mean,
so I'm basically using the OpenEO component to sort of mitigate one of.
I mean, an OpenEO backend basically always comes with a stack machine in some way, because we use internally stack as our metadata format, and we have built on this from the very beginning, basically. And because of this OpenEO, in our case, for example, in Europe, we just recently started also to set up a stack fast API. Before, we didn't have a stack catalog, but we still had a kind of translator that was translating Rasterman collections into a stack representation to pull them out of the data cubes there, and the same on top of Open Data Cube, basically. But yeah, this is backend specific. I think we have to continue with your last one.
If I'm not mistaken, can we save our credits if we are downloading? Then we continue the processing our local.
Yes, absolutely. In the beginning, it makes a lot of sense to a third route that you can that you could go here is really to first use the first couple of lines of this notebook here, where you just do this kind of load collection already with a limited extent, because otherwise it will be expensive nevertheless. But if you already here define your area of interest, and then the next thing could be directly the save result, basically, then you can already store your data and download it. And then once you have your data file in this netcdf format, for example, this would be then the recommended format if you want to go on with the data processing on the client side. Yes. Okay.
It's maybe good to know that with the subscription, you can do quite a lot of requests. Sometimes we see users that are almost afraid of running any request because it will have some cost. But if the cost is a few euro cents, then with the subscriptions that we have, you can actually run quite a bit. So it's not that it's immediately that your company is going to receive huge bills or anything.
Because the first time it was finished so fast. But yeah, maybe now.
Yeah. Okay.
And also you have a network of resources sponsoring, so ESA is sponsoring on top of that.
Good. Then.
The notebook you mentioned is available to us as well.
Sorry?
The notebook you just mentioned, this is in our repository.
Yeah, it's
The one
in
of the-
our repository, and I will point you right now at the end. Let's put it at the end, because I have actually to search, because basically we that was the initial notebook for the FOSS4G presentation we had last year. So. First of all, I would start to thanks Michele, that unfortunately isn't here, that he allowed us to create this notebook, because it's a one-to-one conversion from the OpenEO to the Pangeo stuff. He was really supportive to achieve that. As well, thanks to all the community of the OpenEO that help us to create this event. And as well, all the Pangeo components. So I'm not going to redo all the explanation regarding the notebook in the sense from a more scientific perspective. So we will fly over, but we will focus on the more how you can achieve the same on the Pangeo stuff. So we have the normal import stuff, and then the first step that we need to create is to create the DAS cluster. So instead of using the same approach of OpenEO in which the facility is already organized, you have to basically create your cluster. your worker. So you have to basically ask to the system to organize for you all these components. And to do that, you can easily click on the cell. If you are running on your local machine, don't do that. Okay? No, because then, okay, it's the same? No.
No, it will fail.
It will fail. Okay, sorry. Yeah. One important part that I would stress is this. We are asking to the system to create the workers, but we have to define how many workers we want. More or less, if you are going to use the Pangeo on local, you have the same approach. You can basically ask to the system to do automatically and create the workers within your computer, and he will automatically adapt to the CPU that you have. But time to time it fails. At least in my machine, it fails. So it's much better to define, to ask to the system how many workers I want. So here we ask to create a cluster of 4 workers, and we run. And to have a look, okay, we can see that the 4 worker has been deployed, and you can click at the end for the dashboard. Okay, so I would assume that most of you already know how the task works, but these are the workers, and we will see later how it evolves and how it processes, how you can appreciate that something is happening in the back end. You can as well copy these to the task dashboard, and you have basically the same. Now, this is the old one.
No, it's good. It's good.
Yeah. No, but yes. Okay. This is another alternative to.
You need to copy again you need to copy again dashboard. Control B.
Here you say?
Yeah, you have to copy again.
Sorry, but I'm not used. You're used to.
This one.
Yeah, I have it. Yeah, I have it.
Control B.
Control
V. Enter.
Wait a sec.
Yeah, Control C. Okay, good.
Okay, sorry. Now it's a little bit messy.
Yes. Right, great.
Okay. So what we need is the AOI, and we are going to read the AOI through the GeoPandas, as basically they were doing in the OpenEO. And then here we are using, again, the stack catalog. So what we are going to do is to connect to the stack catalog. In this case, is a stack catalog provided by the Element 84 on the AWS service provider. And we can add some filters, and we are asking to all the data that are intersecting the AOI region that we provided, and the collection we have to define, and as well the time period. Eventually, you can as well add a query to select the cloud cover less than 90. It was, I think. So up to here, what we are doing is absolutely the same as the OpenEO. Nothing more, nothing less. And yep. Perfect. is taking a little bit of time. As you can see, we have 84 assets in the catalog. So now, as this specific catalog doesn't replicate the same names as the normal band 1, band 2, band 3, but they changed.
Why do I have 101?
Because you didn't define the query for the cloud. I changed, as I wasn't, just to make the 101 replication. Yeah, and you have to, okay.
It wasn't free.
Anyhow, you can run with 101. It will be a little bit slower, but that's it. I mean, so if you want to have a look to the assets within the catalog, the query that you did, oops, you can basically remove. No. Sorry. Never work with. So what I would like to show you is that instead of having the band 2, they will name it as blue. Okay, so you must be aware that according to the catalog that you are reaching, it could be that they changed some stuff, some namings, or some, yeah, that's a sort of, I would say, disaster, but...
Don't trigger Peter on IRD now.
Good point. Now, if you want to take an easy approach, you can just use the stack modules to create one huge cube, X-array cube. The only problem is that, as you can see, we have 32 bands and for a total of 4 terabytes. That means that if you would like to use these, you are going to fetch a huge amount of data, okay? So how we can solve it? We can just add some more specification in the stack, and we can ask to limit the research or just pick the data that are within the bounding box that we are defining at a specific resolution. And here we get back to the story of the chunking. Here we can define the size of the chunk. If you don't do that, he will automatically apply a predefined chunk. As well, you can request specific assets. So out of, okay, I have to, yep. Sorry? Yeah, these are cogs, yeah. So that's a good point, because instead of downloading the entire tile or asset, as the cog has already a chunk component in it, he will automatically just retreat the single chunks that we need. So there is the fetch of the data is limited to what you really need. At the same time, you can define the chunk. So if the chunk that they decided from the in the cog is something that you don't really find comfortable for your side, you can redefine. Underneath, basically, there is a GDAC call that will manage all the.
You didn't mention. So
Yeah, no.
this element 84, and I know that they are working with Fox.
No, good point. Yep.
With the resolution parameter, is there resampling done?
Yeah, there is a resampling that you can define in the query. So you have just to define with the raster IO, and then you can select which one is more suitable for your needs. So now, as you can see, it's just 4 giga. instead of before was for 4 tera, so quite something. Up to now, we didn't download anything. We are just playing with the metadata. So the data are still on the server. And now, basically, we start to do what we want to do. So we have to select the specific bands that we want to use and apply the first mathematical formula that we want. We have already a result, but still is a lazy result. So it's still not on our machine or in our cloud virtual machine. To trigger the actual transfer of the data to your cloud or to your local machine, you have 2 options. The first one is to compute, that is actually loading, fetching the data and loading into the memory, the data entirely. The other solution that you have, on the computation, you have to wait until the process has been ended. There is another way, that is the persist, and with the persist, you are free, let's say, to move ahead. So automatically, under the scene, back on the scene, the system will take care of fetching the data and start the computation, but you will be free to get on, to get on, yeah. Okay, never mind. So now we are triggering the persist. Unfortunately, we don't see anything here. We should see something. Oh, okay. Now it's, yeah. Okay. So what I would like to demonstrate here is that actually if I trigger the other computation that we need to do, we are already able to do that. So meanwhile, we have some computation and some fetching from the server. We still can go ahead and elaborate what we want. All the data will remain in each single worker memory. And only once you will request the compute from all the workers will be collected to your machine, to the main access, or how you want to name it. Then we have the mask. And with the mask, we have to, first of all, convert the data, as the data that are in BiDS'24 has to be converted in UTM. Through the GeoPandas, you can easily convert. You have just to define the APSG and select the geometry. And basically, now we have to cookie cut our data. But as Xarray doesn't have the possibility to work with GeoTIFF or vector data, we have to rely on Rio Xarray. So we are just using another module to apply the mask, and we can basically do the same for the snow map, and again we can persist. Now, we've got our data. We cookie cut it. There is one last point that we have to work with, and is the time dimension. As you know, the Sentinels they have a starting acquisition time, and you can appreciate that within the same date, we have different hours. In this case, as we are covering 2 different tiles, we have 2 different times, even though the date is the same. And if we want visualize in just one image, we have to get rid of these, and we have to basically get rid of the time dimension and just keep the date dimension. To do that, we can group by, and we group the data according to the date, and we request the maximum value in the group. Okay, if we have a look, we will see that the name that the bands, the names that now the time has is changed to floor, so we have to rename it, and we can persist again. So we already computed a lot of stuff without really seeing that is happening. And this is happening in our cloud infrastructure. And if we want visualize, we will, is stuck, yeah, because I took too much time. I know, yeah. Yeah. As you can see, nothing is happening here. Okay, but it's the dashboard is really slow. Yeah. No, it's not gray. At the beginning, I thought the same, but in reality, we have some data in here for that specific date. At the beginning, I've got the same impression. I will say, oh, no. There are some data as well. Yes. This morning we had a question regarding why we should use HV plot, and that's the reason. We can change through the slider to different time, or you can define. You can basically define which is the group by that you want use to switch among the data. Yeah, this is much better. Now, Tina will explain you another approach, that is the U function.
So it's just that I talk a little bit quickly about apply ufunc, because that will be introduced on the next notebook. So it's just a teaser of it. So in this example, so we had a lot of calculation that we did here. Like we calculate the green, we calculate the NDC, and then we say that the where, and we select the data, and we do the mask and all of that. In fact, we can group these things basically in one function. For example, like calculate NDSI, snow, cloud. And we basically just copy and paste. Oops, there is a problem here too. Huh? And then we can make a function called like calculate NDC and NI cloud. And then we can apply this function using XRA's apply U function. And one thing we need to take care, because this is here what we are doing is we're using NumPy. So we need, you need to rewrite. Well, basically it's almost the same, but you need to take care that it works with NumPy. And once you make this function, we can apply that using apply function. So exactly same thing that we do the stack. Why didn't you take out the clouds and well, the clouds you already take out, so it's okay. Yeah. And then afterwards we choose the resolution, and then when we apply the stack, you can also define the chunk size. You talked about the chunk size just now. Yeah. And then in this example, what I do is like I separate the chunks of the time. I don't separate the chunks on the direction of this asset. So one for each.
You move the comma, the column.
Thank you. Control Z. So -1, it means we keep all the asset in one chunk, and we keep all the x and y on one chunk. And then and then afterwards we say we all copy and paste every. Fourth dimension here.
The bands.
So the first one is the time, and the next one is the band, and the next one is a x, and the next one is a y. Well, y and x opposite maybe, but.
So the first -1 is the band.
No, it's the time.
This
No,
one,
the
first one is a
first one
time, then the -1 is the band, because I wanted to keep all the band. Because in the, so what we do it is like on the data set, we have the green and then this 3 variable with the three bands. We give the 3 bands, but in the output, we don't have any information about the band. So that means we want to treat the band in the same group. And we want to treat all the x in the same group. We want to treat the y all in the same group. But we want to calculate it by each time slice by time slice. So lasagna, right? Yeah. So that's why I'm keeping this function works for each lasagna. So that's why I'm doing it in this way. So that means when we apply the apply_u function, the input dimension is the lasagna dimension of the band, and y and x is grouped. Output, we don't have any more band. So that's why we only have output dimension as y and x. And then exclude, the band will disappear. So we specify the band disappears. And all these stuff, like we say vectorize true, and we use the paradox, and we use and then another thing is important is like we need to specify what was the type of D type, so what is the, if it's float or if it is the float 32 or 64 or integer and so on, we need to tell them what would be the output format. So, but it's the same as input, output, input, the type, so I keep it, say it's the same as input. So DA is the input data array. And then, well, I say I named it as the name is snow cloud. And then I don't want to keep it as data array. I want to keep it as make it as data set. I say that it will be a data set. The name will be in a snow cloud. Up. So now, so it's apply_u func. It's a great way to like package your series of things you do in one operation. So from the task side, it sees it as just one operation, one graph. So it simplifies for the task to think, oh, I did this and I did that, and then next I have to do this and so on. So it's less swamps task. So it's kind of optimize your workflow. And I guess that's all I want to say.
Okay.
Yeah.
I will basically.
Hey.
Yep.
So do I understand correctly that with this u-func,
Yeah.
it would be a good idea to try to group all your functions you want to apply on a specific chunk together, so that you know already how you can hint
Yeah.
the parallelization that do all these stuff together
Yeah.
on a single
Yeah.
and so it can be like a giant meta function for
Yeah.
all your
Yeah.
functions.
Yeah.
And then the second question,
Yeah.
I noticed you've been using stack here
Yeah.
among the other ODC stack.
Yeah.
Is there a specific reason for this?
We found a really good explanation about what is the ODC stacks, what's the difference, and then I think we put it somewhere, right?
Is in the notebook. Yeah.
It's in the notebook.
Some kind of benchmarking was there.
Yeah. There is I think we put it somewhere on the link on the notebook. Like go. Where was it?
But then, for me, the final, or what I've read a bit, maybe not explicitly, or
Yeah.
maybe between the lines, is that the ODC stack was a bit more mature and maybe a bigger community behind, so I was a bit.
Anybody want to comment?
This is a place where we should try to coordinate the community and work together, right? Because
Yeah.
these are two different implementations that do more or less the same thing.
Mm.
The big difference, as far as I understand, ODCs depends on GDAL, right? And it uses Rasterio under the hood to do screen projection and alignment. And StackStack has a very simple, pure Python-based solution to that.
Where
And
was it?
so it's potentially faster,
We found a
but
great,
also
Yeah,
explanation. I
yeah.
think we put it somewhere.
I don't think so. We discussed about it.
all of NumPy is written in C, right? So, I mean, I don't mean.
I think it's just less dependencies and
I
because of
mean,
this
a
it's more.
GDAL-free
Where?
Cheetah-free.
which is significant, right? I mean, it's a big.
No, isn't.
We didn't add a link.
No.
I stuck ODC.
The challenge though.
No, it should be here and it's not. Okay, we will add. Okay.
Yeah.
So maybe we can talk offline, but it would
Yeah.
be really good to
Yeah.
compare
Yeah.
the capabilities and get the
That-
communities talking.
So there was a really good issue comparing about this ODC stack, what is good and we thought we could put the link on this notebook, but we don't find it. It's Alejandro who found it. That's this.
Yeah.
Yeah. And then, so, yeah, we will update our notebook this evening, and you will have you seen this you seen that one? Yeah. Okay. So
But
you
we
know
are
the
already-
story.
yeah.
Yeah.
And I was just interested in your point of view and why this. Was it a coincidence that it was that I've seen it twice?
Yeah.
or-
Yeah.
Okay.
Yeah, it's just we started to make a notebook with a stack because
Yes,
that would
and
create more the data array so that we could have all the three bands in one data
That's one
array.
of the differences.
Yeah. And then
Another difference was I've seen that interesting in the one was not taking into account, to my knowledge, the scaling and the offset yet.
yeah,
Was not implemented. I think the ODC stack was not yet implemented.
Mm.
But then, because that's an issue in the Sentinel too, that after this H05 baseline, suddenly there was another offset.
okay.
If you start combining both, you really want this.
Yes,
We
that
could
was
start
something
to
like
talk
that.
about ARD data to
I think we
avoid
need
these
to go
kind
on
of.
also, otherwise.
Yeah. So we can discuss it offline later on. Yes, sure. Why
How
you
we
lost
can
it?
conclude this?
No, there was a. you
No, we
didn't-
will skip. I mean, we are already
Okay.
a little
Okay.
bit too late.
there's
So
a-
I hope that you didn't experience something like this. To wrap up, and that's my personal opinion, the difference between OpenEO and Pangeo, just to have a quick understanding. This is OpenEO, okay? It's nice. You can do a lot of stuff. Really nice, but what's Pangeo? Pangeo looks like more this. And actually, I point exactly this stuff. The power that you have on Pangeo is that you can, from the other communities, add stuff on it. So work with other modules that are not available in Pangeo, okay? So you can bring your beer with this car up to a certain point, and then definitely you have to use this. There is only one problem. Time to time, working with the Pangeo X-Array task can be tough as drive this type of car, okay? Maybe you are better than me, but just to, if you get stuck, I have to say that is kind of normal. The last difference that I won't stress is the cost. If you use Pangeo stuff and you have a facility in your company or in your university, you are free to do stuff basically once you have the data close to you for free, okay? So one of the biggest issues, you can prototype with OpenEO on your laptop, but if you need to scale it up, you have to pay. It's not true that you don't have to pay as well in a certain vision with the Pangeo stuff, because basically you are running stuff. Again, if you have an HPC, you are running stuff, and you have to be careful because this means electricity, and this means costs as well, or maintenance, and so on and so forth. Is not the last word is not or Pangeo or OpenEO. I would dream to see an and. So on, let's say, the CDSC, I would really like to see an and, not an or. Is not a fight, is that just that the community has to work together to provide the better that we can offer to the users. That's my conclusion.
Small question.
Go ahead.
Newbie to the field, but I've looked up OpenEO, and then there's also EO Learn, which is another seems to be sophisticated package.
Yeah.
Is this because you're talking about community and working together? Is this a completely different thing, or is this?
It's quite different, EO Learn. It's from the colleagues at Synergize Planet. And it's a Python library that works actually with Sentinel Hub in the back to retrieve data, for instance. And then also with a focus on machine learning, I think. So yeah, it's different, to give the short answer.
But there is some plans to connect this in the future to make use of this nice library within.
Okay.
There's the Open Earth Monitor project. It's a Horizon Europe project where this is realized right now.
Combine all of these in a way.
On the machine learning aspect, at least, to get some of the functionality from EO Learn into OpenEO as well. Yes.
Okay. Yeah. Thanks for.
Maybe as a short intermezzo, one of the things we also do is generating this kind of stack metadata for you. This is also where we are complementary, because we see stack a little bit as the glue between various systems. One system reads data from stack, but again produces data. And if you properly get the stack metadata right, then the next system can go on and read your produced data again and do something with it. So that is like the glue between things. But it does depend on everybody creating this nice stack metadata correctly, which is not so easy. So that's what we do. We do it, starting, of course, from those nice principles that you find on the FAIR website, which are quite abstract. And we take those and try to generate metadata that actually complies to it. And then if you open it in a tool like Stack Browser, it looks like this, for instance. And here is the JSON. But let me now take the OpenEO editor, which is also just showing it. And then you see that we, for instance, you have the nice assets in here. You also have the lineage, the processing graph or algorithm that was used to compute this. The raster band metadata statistics, but also and that's a very nice one, the input source files. So for reproducibility, this is key, that you actually know, like this black box platform that I was using, what input products did it use to compute this result? Because this can be key when you are trying to figure things out later on, like something is wrong or different. Then it's often the first thing you want to do is look at the things that went in there. And here it's, for instance, Sentinel-1 GRD data together with Sentinel-2. That was a short thing on metadata before I do the heavier stuff again. Wait, let me see. No, here. Here. Yeah. So it's about user-defined functions. And this is one of the points next to the nice client-side processing where we have this huge complementarity. Because actually what user-defined functions are actually implemented in Python based on Xarray. So then we are right there in the Pangeo world. So you can take your Pangeo algorithm based using Xarray, using NumPy, and run it also in the backend. Again, with this whole workflow that we discussed, you first debug, test interactively, locally on your laptop, and then when you're happy and you want to scale out, but maybe you want to do it on a data set that is in OpenEO, but does not have a stack catalog, so you cannot readily get it on a DAS cluster, or you don't want to manage the DAS cluster, then you can still use the OpenEO backend to run your Pangeo X-array algorithm. So that is the whole thing behind user-defined functions. So you really, for scaling up, that it's useful. For local debugging, there we for sure say just do it on your laptop. There's also some general guidelines on when and when not to use UDFs. It's mostly when you already have your algorithm implemented in like source code lying around and you don't want to re-implement it fully, either usually because you don't have the time, or it's so complex that you don't want to do all the testing and it has a lot of dependencies and so on. And that's often when you do UDFs. On the other hand, when you're of course starting from scratch, then it's worth trying to use the OpenEO predefined functions. And the main reason for that is the whole reproducibility that we try to achieve. We try to make you technology independent. That is one of the key things. And of course, you're not going to achieve that if you use a specific library. That's of course not saying it's forbidden or anything. It's just the general reproducibility angle there. Also, for the highest possible level of portability, the UDFs are a less good option, of course, as long as the backend supports running Python code, which is not that hard, then they can still work. There's also this story here that we also see it a bit as a way for the user community to help us design those OpenEO processes. In OpenEO, you saw that we have a bunch of predefined processes. Some of them are fairly easy, some of them can be more complex. What you can do with this functionality is actually test and implement your own process in Python, like you're doing it already probably. And then if you have a nice modular building block where you say, hey, this would be nice to standardize, then you can actually come to the community and ask us, hey guys, would it be a good idea to convert this into a predefined process? And if you have actually tested it already, like in terms of what parameters does it need, what goes in, what comes out, you have a well-defined code, then that process of standardization is a lot easier to do, in fact, because you can start from code and don't have to imagine it and write a specification. So that's also a very nice use case and thing that is allowed by these UDFs. So that's the theory, so to speak. Then we have a few examples, really just to show you how it looks like. If you really want to use them, I just recommend actually using them. Let me see, should I just take the notebook here? This one is about peak valley detection, which is a remote sensing technique. You have a time series that it goes up and down, so you have peaks and valleys, and you want to detect where they are. So what did we do? Yeah, I'll not run too many cells here. We compute a very simple NDVI, and then we have this code, and the code is actually already there. So if we have downloaded it as a netcdf file and locally, then this library just runs on the X-array locally, and you get your result. Oh wait, that's what I was doing here. And the cool thing is that we designed it so that it can also run on your OpenEO data cube, and I will show that in a minute. Maybe just to quickly cover the algorithm. These are the NDVI images of multiple observations. And here, actually all the way at the end, are two plots that are the same. And the only difference is that one of them was generated on the OpenEO side, and one of them was generated just on my laptop, actually. And of course, the detected peak valley events are the same. If I then go into the actual code, let me see, where am I? Here. I have a Python file, it's this one. This is in a separate Python file, because for the OpenEO UDFs to work, we actually need to load the Python code as one big text block and send it over to the backend. That is what we basically do. And the entry point is here. So you have a function with a predefined signature that you always just copy and paste. And it takes in a cube, which is a wrapper around an X-array object, and it also returns the same object. And what goes in between is basically just whatever code that works with X-array. So it can really be anything. This is time series analysis. So if we really go towards the code, then you will see that we do this nice apply ufunc. So we use apply ufunc to run an algorithm over the time dimension while we're not really caring about the other dimensions that happen to be in that data cube.
Is there any other way that is more user-friendly than this apply u function from this?
As it happens, I was actually thinking of, hey, can't we do this more easily? And there could be a way. We could actually just still do the apply ufunc, but hide it for you, that it's done in the OpenEO backend and that you no longer do it yourself. And it would involve creating a signature where we say, okay, here you get the actual time series for a pixel, and then you run over it. It's just that you always have to be careful in Python when looping over many things that it remains efficient, of course. So we would have to test with it that it's properly done. We can't just go write a for loop, but that's what apply ufunc normally solves for us. And then I think it could work, yeah.
Another path is to just try and make that apply ufunc more user-friendly.
Yeah.
None of these libraries are fixed in stone, right? So if there's ways it could be simplified into sharp edges, like X-ray is also evolving, right? It's not.
Yeah, I mean, for me it was really a surprise, you know, when I started with X-rays that there is no something like this already there. So I have to go to NumPy to do this.
There's map blocks.
Yeah.
Right?
Yeah.
So map blocks is kind of like apply ufunc, but you keep the X-ray data structures. You don't have to write NumPy. They're different use cases.
Okay. What else is in here? We also see how we actually invoke the UDF on the OpenEO data cube. It's in the same file because, in fact, we do this thing, this trick somewhere in the beginning. Where is it? Where was it again? Yeah, maybe. It's just that when we see that it's an OpenEO data cube, then we go into this code path where we actually do the apply dimension over time. So this single line is actually where the UDF gets loaded from a file and sent off to the backend for execution. So that is the whole thing, actually. Yeah, that's it. And that's how we can fairly transparently even write libraries. This is coming from the FuseTS library that really work both on X-array objects and OpenEO objects just at the same time, even. Like we can hide it for the user. Last example for the day was about machine learning, just because it's so popular. Yeah, of course. This one is about parcel delineation. It's also using user-defined functions. And parcel delineation, so the output looks like this. You have agriculture, and you have these plots where farmers are having their crops, and you want to detect them, right? That's the problem statement here. So we solve that with AI nowadays, like any other problem. And what the AI algorithm needs is this nice spatial temporal chunk. So not only a single pixel time series, but it actually wants to look at also the spatial context and with some overlap between spatial chunks. Because otherwise, for a problem like this, if you don't have overlap, then you would see the chunks basically where your algorithm was being run on. So you want to specify an overlap area of having some pixels overlapping between chunks, so that you can have a nice continuous prediction of your algorithm. And that is what we do in OpenEO with the apply neighborhood function. Let me go back here. So this is specifying an area of a certain size and x and y dimension, and then also a certain overlap. The time and band dimension are not included, which means we just take all observations over time. So this will get all of them as input, this whole stack of an 128 by 128, I think it's going to be in the end, kind of like data chunk, that you then feed into your model, and you get your segmentation out of it. And then later on we run I think a simple raster to vector thingy to get the actual vector files. So you can also do that kind of thing with these things, and it heavily relies on, again, the UDFs, because all these nice deep learning libraries, here it's TensorFlow, I think, just work with NumPy interfaces basically, so it's easy to connect them together that way. That's it. I'm not going to dive more deeply into that one. Just now that we're on the topic of machine learning, what you often then also need to do is sampling data sets, meaning you have training data like Lucas, which has points all over Europe, and you want to extract points for learning. And then what we typically recommend is that you kind of group your points spatially. We don't recommend to run it all of Europe at once. It's going to be a bit large for even that we cannot handle. So you create these nice spatial groups, points located together, and then you can send them off as batch jobs to the OpenEO backend to get, for instance, a CSV file with all the inputs per points. Of course, if you're training the model I showed just now with the spatial areas, then you don't need point data, then you need to extract chunks as netcdf files, for instance, and that also works. So then you just get a netcdf file per data chunk that you want to have, and you can also do it all over Europe if you want. That goes a bit with that story. Okay, then now it was almost time to wrap up normally. We do have the under the hood thing, and we covered a nice, some topics already today, so that's nice. The thing is that actually everything you learned about chunking and so on also very much applies to OpenEO. Like here in our backend, it's called partitioning, and the screenshot even resembles a little bit some of the things you saw going on in Dask, with tasks being executed and this graph being created. The underlying theory is basically the same. What we sometimes try to do in OpenEO is trying to predict the chunking. This is like the automatic setting that we saw also, I think, and hide it from the user by analyzing the process graph. But the reality is that also that doesn't work all of the time. So, and then what you get is the same as with Dask, that you get either it runs very slow or it goes out of memory and gives you very weird errors. That is the under the hood story there. So it's very much the same. Also, the performance-wise, that's maybe a good one still. So why is it so much faster for running small things on your laptop rather than sending it to the cloud? On the cloud, we actually, for instance, in CDSE, but also many other backends on AWS or at Vito at Terrascope, we go back to these network file systems with the original Sentinel-2 files, or even Sentinel-1 as backscatter, not as backscatter data, but as raw, not georeferenced data sets. And then you have to fetch them from there, and that is very slow, because if you're doing time series analysis over multiple bands, then this can mean that you have to really read from thousands of files, literally, on this network file storage. And even though it's quite fast, it's not that it's very bad or anything, it's just the sheer volume of data access that you have to cover, even when doing it in parallel, that is taking this time. And that is why it takes minutes to assemble this nice netcdf file. And then once you've downloaded it, and it's in this format and much smaller, start on the SSD drive of your laptop, then opening that is super fast and of course much more performant than OpenEO. That is a very a key thing in this understanding of why it's so slow. Also because we see, or sometimes you see people focusing a lot on the processing speed and CPU and whatnot, while it's just the I/O that is being the bottleneck and that's blocking you.
Just one question regarding this happens, I would say, time to time. As behind this, there is a sort of cost. The system will recognize that the error wasn't on the user, or it will anyhow count it in the user.
Yeah. For now, it's anyhow counting it.
Okay.
Because it's, for instance, if it goes out of memory, yeah, then because you can tune memory as a user. You can request more memory. So it's also a setting you have to do, and you have to get right. And that is the reason why we generally recommend that you start on small areas and then start scaling them up, so that you do not run a huge costly job that would cost a lot. Well, actually that hardly exists. I mean, most jobs that I see, the bigger ones, cost a few euros, so to speak. So if they fail and you notice, yeah, then please stop running them and don't keep on sending failing jobs to us, because then your bill would indeed accumulate without getting results. But most people realize, like, hey, something's wrong, let's stop here and try to fix it.
How large will a bigger job be? What would you define as one of those bigger jobs?
Currently, so the size that we test a lot on is, we usually stop at like 100 by 100 kilometer tiles, but then it also depends a lot on how far you go in time. Are you running over a year or less? Like when we generate the European crop type maps, we run on 20 kilometer tiles, and that's taking data for like 9 months or so, I think, per execution. And then those jobs run in 20 minutes, so they're not huge. And the reason we prefer to have them small is also to have more control, more cost control, and less wasted money and resources when things go wrong, in fact. So even though we test a lot up to this 100 by 100 kilometer area, often depending on how long the jobs then take, we try to keep them smaller so that they finish in under an hour or under half an hour. That's just a convenient way to work.
Do I understand this correct? You do 20 by 20 for the crops, and then you go over all of Europe?
Yeah.
Chunk by chunk?
Yeah, it's like 11,000 20 by 20 tiles or so. Yeah. But we run many.
That would only, and then every 20 by 20 would cost a couple of euros.
Less, I think. In that example, it's less. Yeah.
No,
it's. I think there it's around €1 per tile in that order of magnitude. Yeah. Yeah. So we just go all over Europe, and that works.
So all of Europe, that's still quite a bit.
Yeah. If you generate continental maps anywhere or global maps, it's relatively costly. And then of course I'm talking about running on EU infrastructure, not on Amazon with special pricing and whatnot.
Yeah.
There is also a bit of a difference. Not sure if here. You can of course read all of this is online. We even have the architecture for people that want to run it themselves, like it's really on Kubernetes and so on. And also those performance tips of keeping your data cube keep the size a little bit in mind, that also matters. That's actually what I was saying. If you're going to go very huge, then yeah, you'll be sending mails like, hey, my job is running for 4 hours. Then usually it's try to make it smaller somehow. It's just not so convenient. It can work. It can maybe still finish after 10 hours. It's just not so convenient for you to work like that. That's it. I think I'm going to wrap up here.